Part 1. The motion you cannot feel right now, without any sensation of movement whatsoever, without any wind against your face or vibration beneath your feet or hum through the floor beneath you. You are traveling through space at a speed that would be almost impossible to hold in your mind if you genuinely tried to picture it in human terms. Not just moving, hurtling, carried along by forces operating at scales so enormous that the entire span of human civilization, every empire and every century, every war, and every technological revolution from the first stone tool to the present moment represents less than a blink of an eye against the timescale on which these forces have been acting. The motion starts locally with the rotation of the Earth. If you happen to be near the equator, the surface of the planet is sweeping you eastward at approximately 1,674 kilometers per hour. That number, written plainly, is already extraordinary. The speed of sound in air at sea level is roughed 1,235 kilometers per hour. You are being carried at nearly a third faster than the speed of sound, constantly, right now, and your body registers none of it. No wind, no roar, no sensation of velocity. The air moves with you. The ground moves with you. Every object in your environment moves with you at the same rate, and so there is no relative motion between you and your surroundings. No gradient that your senses can detect. Nothing to distinguish sitting in a chair on a rotating planet from sitting in a chair in empty space. This is the first layer of invisible motion. But it is the smallest one by a significant margin, and understanding why we cannot feel even the first layer is essential to understanding why the largest layer, the one we will spend most of this video exploring, is equally invisible, despite being orders of magnitude greater in speed. The reason none of this motion registers is a principle so fundamental to physics that it underlies virtually everything in the science of motion, the principle of inertial frames. When you are inside a system that is moving at constant velocity, with no acceleration, no change in the rate or direction of motion, every physical process inside your system behaves exactly as it would if you were at rest. A ball thrown upward inside a smoothly moving train follows the same arc it would follow in a train sitting in the station. A pendulum swings with the same period. A cup of coffee sits still on the table without sloshing. The laws of physics are identical in all inertial frames, and there is no physical experiment you can perform inside an inertial frame that will reveal your absolute velocity. You can only measure your velocity relative to something outside your system. This is why the motion of the Earth, for all its enormous speed, is completely invisible from within. The Earth is not accelerating in any direction that your body can easily detect. At least not in its rotation and orbital motion. The rotation produces a tiny centrifugal effect, barely measurable, and the orbital motion around the Sun produces a tiny Coriolis deflection in the trajectories of large-scale atmospheric flows. But these are subtle second-order effects. The primary velocity, the 1,000+ kilometers per hour of eastward motion at the equator, is completely imperceptible because it is constant and your entire environment shares it. Now, the Earth is also orbiting the Sun. The average orbital speed of our planet as it traces its elliptical path around the Sun is approximately 30 kilometers per second, not kilometers per hour, kilometers per second. In 1 second, the Earth moves 30 kilometers along its orbital path. In the time it takes you to blink, which is roughly 150 to 400 milliseconds, the Earth has moved somewhere between 4.5 and 12 kilometers in its orbit. Over a single day, Earth travels about 2.6 million kilometers. Over a year, its orbital path covers approximately 940 million kilometers, and you feel none of it, for exactly the same reason you feel none of the rotation. The Sun itself is not stationary within the Milky Way. It is orbiting the galactic center, dragging all its gravitational family along with it. All 8 planets, all their moons, all the asteroids and comets and trans-Neptunian objects. The entire Oort cloud extending out nearly 2 light-years from the Sun. The Sun's orbital speed around the galactic center is approximately 230 kilometers per second. At this speed, it takes the solar system roughly 225 to 250 million years to complete one full orbit of the galaxy. The Earth is approximately 4.6 billion years old, which means the solar system has completed somewhere between 18 and 20 galactic laps since the Earth formed. Each of those laps took approximately the same length of time as the entire Phanerozoic eon, the entire span of complex multicellular animal life on Earth, from the Cambrian explosion to the present day. The solar system orbits the galaxy at a pace so slow that complex life has enough time to originate, diversify through hundreds of millions of species, survive 5 major mass extinctions, and give rise to intelligence within the span of a single orbit. And yet this too is invisible, unfelt, undetectable from inside the moving system. Now we arrive at the layer that is the subject of this video. The Milky Way galaxy itself is moving, not orbiting within some larger structure in the way the solar system orbits the galactic center, moving. The entire galaxy, the full 100,000 light-year wide disk of it, all the spiral arms and the central bulge, and the dark matter halo stretching out tens of thousands of light-years above and below the disk, all of it is moving through the universe at approximately 627 kilometers per second. This works out to more than 2.2 million kilometers per hour. To try to make 627 kilometers per second feel real, in the time it takes you to read this sentence aloud at a comfortable pace, roughly 5 seconds, the Milky Way moves about 3,135 kilometers. In 1 minute, the galaxy travels approximately 37,620 kilometers. In an hour, roughly 2.26 million kilometers. This is a speed at which you would cross the diameter of the Moon, 3,474 kilometers, in about 5.5 seconds. It is a speed at which you would circumnavigate the Earth's equator, 40,075 kilometers, in about 64 seconds. At this speed, the entire galactic disk, 100,000 light-years from end to end, would move a distance equal to its own diameter in approximately 160 million years. On cosmic timescales, this is a brisk walk. The direction of this motion is specific. The Milky Way is not drifting randomly. It is pointed like an arrow toward a specific location in the southern celestial hemisphere, toward the constellations Centaurus and Norma. There is a gravitational destination, or rather a set of destinations, stacked at different distances, that have been collectively steering the galaxy for billions of years. But here is what makes this genuinely astonishing to contemplate. Nobody on Earth has ever felt this motion. Not today, not yesterday, not at any point in human history. The rocks beneath your feet are not vibrating with it. The ocean does not lean to one side under the influence of it. Your body is not compressed or stretched by it. There is no cosmic wind howling past the planet as it moves at 627 kilometers per second through the universe, because there is no medium for the galaxy to move through in the way a ship moves through water. Space is not an obstacle. Space is the stage. The galaxy moves through it, and from inside the galaxy, the motion is as invisible and unfelt as the Earth's rotation is from inside a smoothly moving room. The only way to detect it is to look outside, to find something external to the galaxy, some reference against which the galaxy's motion can be compared, something that is not moving with us and from which our velocity can be inferred. Such a reference exists. It is the oldest light in the observable universe, and it fills all of space equally. When the universe was approximately 380,000 years old, it underwent a transition that cosmologists call recombination. Before this moment, the universe was hot enough that hydrogen atoms could not remain neutral. Every hydrogen atom that formed was immediately ionized again by the ambient radiation field. Electrons and protons existed as free particles in a plasma, and photons of light were constantly scattered by the electrons, bouncing around in the plasma like light in a hall of mirrors. The universe was opaque to light, in the sense that any given photon could not travel very far before being absorbed and re-emitted. Then, as the universe expanded and cooled to about 3,000 degrees, protons and electrons recombined into neutral hydrogen atoms, and the universe became suddenly transparent. The photons that had been scattered and rescattered for 380,000 years were abruptly free to travel in straight lines without further interactions. They have been doing so ever since. Those photons are still traveling today. After 13.4 billion years of travel through an expanding universe, they have been stretched and cooled to a temperature of approximately 2.72 degrees above absolute zero, placing them in the microwave range of the electromagnetic spectrum. They fill all of space uniformly, arriving at Earth from every direction with essentially the same intensity and temperature. This is the cosmic microwave background radiation, or CMB, discovered in 1965 by Arno Penzias and Robert Wilson at Bell Telephone Laboratories in New Jersey, initially as an unexplained noise signal in their horn antenna. The CMB is the closest thing in nature to a perfectly uniform reference frame. It fills the universe uniformly and isotropically, the same in all directions to very high precision. Any observer who is truly at rest relative to the average matter distribution of the universe would see the CMB as perfectly uniform in temperature from all directions. Any observer who is moving relative to this average would see the CMB as slightly hotter in the direction of motion because of Doppler blue shift and slightly cooler in the opposite direction because of Doppler redshift. When astronomers measure the CMB from Earth, they observe exactly this pattern. After subtracting the effects of the Earth's orbital motion and the Sun's motion around the galactic center, they find that the Milky Way itself is moving at approximately 627 kilometers per second relative to the CMB rest frame in the direction of the southern sky. This measurement has been confirmed and refined by multiple space missions including COBE, WMAP, and Planck, and it is one of the most precisely and confidently established facts in modern observational cosmology. What is pulling the Milky Way to produce this motion? The investigation of that question, which has consumed the careers of dozens of the best observational cosmologists of the past half-century, is one of the great detective stories of modern science. It involves gravitational forces acting across hundreds of millions of light-years, structures so massive they defy easy comprehension, a discovery that gave the Milky Way a new cosmic address, a void so large its absence of mass acts as a repulsive force, and unresolved questions about whether the ultimate source of the cosmic flow might lie beyond the edge of the observable universe itself. The river has been running for longer than the Earth has existed. We have only just begun to see its banks. Drop a comment right now and tell me where in the world you are watching from and what time it is. It is always remarkable to see how far these videos travel. And if you have not subscribed yet, this is a good moment to do that, because everything we are about to uncover about the structure pulling our galaxy across the universe is going to keep building. Part 2. Mapping the Invisible River. The Discovery of the Flow. To understand what is pulling the Milky Way, it is first necessary to understand how the universe is organized at the largest scales, and why the process of mapping that organization took most of the 20th century and required the development of observational tools that did not exist at the time the question was first posed. The universe is not a smooth, uniform distribution of galaxies scattered randomly through space. Even the earliest systematic observations of galaxy positions made clear that galaxies tend to cluster, to collect in groups and associations, rather than being distributed evenly. But the full scale and architecture of that clustering was not apparent until large redshift surveys in the late 20th century revealed for the first time the three-dimensional structure of the universe out to hundreds of millions of light-years. What those surveys revealed was something called the cosmic web, a vast network of galaxy filaments and sheets surrounding enormous regions of near emptiness called voids. Galaxies congregate along the filaments, cluster at their intersections, and are largely absent from the voids. The overall pattern, when visualized in 3 dimensions, resembles the structure of foam, or a sponge, or the branching network of a neural system. Concentrated matter at the nodes and along the bridges, vast hollowness in between. And this architecture is not random. It is the direct consequence of gravity acting on the initial conditions set down in the Big Bang, amplified over billions of years into the elaborate web we observe today. Every node, every filament, every sheet in this web is a gravitational attractor. Matter flows toward the denser regions along the filaments, from the voids into the sheets, from the sheets into the filaments, and from the filaments into the clusters and superclusters at the major nodes. This flow is slow by human standards but relentless over cosmic timescales, and it is responsible for the peculiar velocities of every galaxy in the observable universe, including the 627 kilometers per second that the Milky Way carries toward the southern sky. The challenge for astronomers of the mid-20th century was that they could not easily see this web for 2 distinct reasons. The first reason was technological. Building a comprehensive 3-dimensional map of the universe requires measuring the redshifts of millions of galaxies across the entire sky, which in turn requires large telescopes, efficient spectrographs, and enormous amounts of observing time. The technology to do this at scale did not exist until the 1980s and 1990s, when digital detectors replaced photographic plates. Fiber optic multiplexing allowed simultaneous spectra of dozens or hundreds of galaxies in a single telescope pointing, and large automated surveys became feasible. The first surveys that revealed the cosmic web in recognizable form, the CFA surveys led by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics, the 2DF Galaxy Redshift Survey, the Sloan Digital Sky Survey, all came in the latter decades of the 20th century and the early 21st. The second reason was more specific and more frustrating. The direction in which the Milky Way's peculiar velocity was pointing, the direction toward which the gravitational current was carrying us, happened to coincide with one of the worst obscured regions of the sky, the zone of avoidance, the band of sky where our own galaxy's disk blocks the view of the more distant universe, ran directly through the region that most needed to be surveyed. The primary attractor, whatever was pulling us, was hiding behind our own galaxy. The zone of avoidance exists because we are inside the Milky Way's disk, looking outward through it. The disk contains hundreds of billions of stars, enormous quantities of molecular gas, and above all, dense concentrations of interstellar dust. Interstellar dust is made of tiny solid grains, silicates and carbonaceous compounds and organic molecules, with sizes comparable to the wavelengths of visible light, and it absorbs and scatters visible photons with great efficiency. Looking through the galactic plane in visible light is like trying to read through a thick stack of ground glass. Galaxies even a few 100 million light-years behind the plane are reduced to invisibility. The zone of avoidance covers roughly 20% of the total sky, and that 20% includes the most dynamically significant direction in our cosmic neighborhood. This is one of history's more inconvenient arrangements of the furniture. The very thing blocking our view, our own galaxy, contains the vantage point from which we are trying to look. It is as though the most important geological features on Earth were all located directly beneath the thickest cloud layers, permanently out of sight. The first major attempt to characterize the peculiar velocity field of the nearby universe and identify its dominant attractor was made by the group of 7 astronomers now called the Seven Samurai: Sandra Faber, Donald Lyndon Bell, Roger Davies, David Burstein, Roberto Turlevich, Gary Wegner, and Alan Dressler. Beginning in the mid-1980s, they conducted a systematic survey of the peculiar velocities of elliptical galaxies across a large region of sky, using the fundamental plane method to estimate true distances and thereby extract peculiar velocities. The fundamental plane is a three-way correlation between the size of an elliptical galaxy, measured by the effective radius containing half its total light, its surface brightness, meaning the amount of light per unit area, and its internal velocity dispersion, the spread and velocities of its stars as measured by spectral line broadening. These three quantities are correlated because elliptical galaxies are in dynamical equilibrium. Their stellar orbits balanced against their self-gravity, and the physics of that equilibrium constrains the relationships between these observables. By measuring the velocity dispersion and surface brightness of an elliptical galaxy, you can predict what its effective radius should be, and comparing that predicted radius to the observed angular size gives you the distance. This distance is independent of the galaxy's redshift, so you can subtract the Hubble flow contribution and extract the peculiar velocity. The technique has an uncertainty of roughly 15 to 20% per galaxy, which means individual galaxies have noisy distance estimates. But with hundreds of galaxies in the sample, the statistical noise averages down and the underlying flow pattern becomes detectable. The Seven Samurai measured distances and peculiar velocities for over 400 elliptical galaxies, a sample large enough to reveal the coherent flow pattern that became their most significant result. What they found, published in 1987 in a series of papers that attracted immediate and sustained attention, was that the peculiar velocities of elliptical galaxies across a region, spanning hundreds of millions of light-years, were not random. They showed a clear, directed flow toward a specific region of the southern sky, in the direction of the constellation Centaurus, at amplitudes of hundreds of kilometers per second. The galaxies were flowing, coherently and measurably, towards something that the Seven Samurai could not directly see, but could infer from the direction and amplitude of the flow. They estimated that the object responsible had a mass of something like 10,000 trillion solar masses, concentrated at a distance of roughly 150 to 250 million light-years. They named it the Great Attractor. The name entered the astronomical vocabulary immediately and has stayed there ever since. The Great Attractor became one of the iconic mysteries of modern cosmology, a gravitational behemoth hiding in the zone of avoidance, pulling on galaxies across hundreds of millions of light-years, invisible to optical telescopes, inferred only from the directed motion it produced in the matter around it. But identifying the Great Attractor as a gravitational anomaly, as a flow convergence point, was only the beginning. To understand what it was made of, what structures were actually responsible for the observed flows, required decades of follow-up work using instruments and techniques that were still being developed at the time of the Seven Samurai's original publications. The tools that eventually penetrated the zone of avoidance fell into three categories. First, radio observations at 21 centimeters, the wavelength of the neutral hydrogen spin-flip transition, could detect the radio emission from hydrogen gas in galaxies even through the galactic plane, because radio waves at this frequency are not absorbed by dust. Using radio telescopes to map hydrogen emission across the zone of avoidance revealed galaxies hidden from optical view. Second, near-infrared surveys using wavelengths slightly longer than visible red light, in the 1 to 2 micron range, experienced much less dust extinction than optical surveys and could penetrate significantly deeper into the zone of avoidance. The two-mass survey and subsequent near-infrared projects built extensive catalogs of galaxies at low galactic latitudes. Third, X-ray satellites in space, above the atmosphere and above the galactic dust, could detect the hot intracluster gas of massive galaxy clusters through the galactic plane, because X-rays are not scattered by the same dust that blocks visible light. Using all three approaches, and particularly using X-ray observations from the Rosat satellite, astronomers in the mid-1990s identified the dominant structure in the Great Attractor region. It was a massive galaxy cluster, designated Abell 3627 in George Abel's catalog of rich clusters, also called the Norma cluster for the constellation in which it appeared. Renée Cron-Cordaweg and her collaborators conducted extensive optical surveys at low galactic latitudes and identified hundreds of previously uncatalogued galaxies associated with it. Hans Boehringer and the Rosat team characterized it in X-rays and confirmed its enormous mass and high gas temperature. The Norma cluster, sitting approximately 220 million light-years away behind the galactic plane, was the hidden monster the Seven Samurai had predicted. But the Great Attractor story did not end with the identification of the Norma cluster. Almost immediately, it became clear that the Norma cluster, massive as it is, could not by itself account for the full peculiar velocity of the local group. The flow extended beyond it, and the Great Attractor region itself was moving, being pulled by something even farther away. The river had a source deeper than the first waterfall, and following it would require looking beyond the zone of avoidance toward a structure that Harlow Shapley had noticed as a vague concentration in photographic plates 90 years ago. Part 3, The Great Attractor Unveiled, Abell 3627 and the Hidden Monster. The full story of the Great Attractor's identification is a story about persistence, about the development of new technologies, and about the scientific community's determination to see through the physical barrier of our own galaxy to find what was hidden behind it. When the Seven Samurai published their landmark papers in 1987, they could characterize the Great Attractor only as a flow convergence point, a location inferred from the direction and amplitude of the peculiar velocities they had measured. They knew its approximate direction, roughly toward galactic longitude 320 degrees and very close to the galactic plane. They knew its approximate distance, somewhere in the range of 150 to 250 million light-years. They estimated its mass at something like 10 quadrillion solar masses, but they had no specific structure to point to. The object responsible for the greatest known gravitational anomaly in the nearby universe was invisible. The challenge was fundamental. The galactic plane in the direction of the Great Attractor is among the most heavily obscured regions of the sky. The dust column in this direction is dense enough that even galaxies relatively nearby behind the plane, within a few hundred million light-years, are reduced to invisibility in optical surveys. Standard galaxy catalogs, which were built primarily from optical photographic surveys, simply had no data in this region. There were no bright galaxies to catalog, no galaxy clusters to identify, no redshifts to measure, because the foreground of our own galaxy's dust was blocking everything. The first concrete evidence for structures in the Great Attractor region came from the IRAS satellite, the infrared astronomical satellite launched in 1983. IRAS surveyed the entire sky in 4 infrared bands, ranging from 12 to 100 microns wavelength. At these wavelengths, the dust that blocks visible light is much less opaque, and galaxies emitting strongly in the far infrared, because of warm dust heated by star formation or active galactic nuclei, could be detected even at relatively low galactic latitudes. IRAS-based galaxy surveys, developed by teams including Will Saunders, Michael Rowan Robinson, and their collaborators, identified density enhancements in the zone of avoidance consistent with the expected location of the Great Attractor region. Radio surveys at 21 centimeters also contributed. Neutral hydrogen emission from galaxies is entirely unaffected by interstellar dust, and systematic surveys with radio telescopes tuned to this frequency could detect galaxies behind the galactic plane regardless of dust extinction. The HIPASS survey and its predecessors mapped a significant population of gas-rich galaxies in the zone of avoidance that had no optical counterparts in existing catalogs. The X-ray confirmation was perhaps the most decisive. The Rosat All-Sky survey, conducted between July 1990 and January 1991 by the German-British-American X-ray satellite Rosat, produced the first comprehensive X-ray map of the entire sky with sensitivity to extended sources such as galaxy cluster halos. The hot intracluster gas in a massive galaxy cluster, heated to tens of millions of degrees by gravitational compression and the kinetic energy of infalling material, radiates copiously in the X-ray band. This emission can be detected even through the galactic plane, because X-rays at the energies emitted by cluster gas are only partially absorbed by the interstellar medium, and with appropriate absorption corrections, the cluster can be identified and characterized. When Hans Boehringer and his team at the Max Planck Institute for Extraterrestrial Physics analyzed the Rosat data in the direction of the predicted Great Attractor Center, they found a bright, extended X-ray source. Its position, distance is estimated from the redshift of associated galaxies, and X-ray luminosity and temperature all were consistent with a massive galaxy cluster at the predicted location of the Great Attractor's core. This was Abell 3627, the Norma cluster, and its X-ray characterization confirmed beyond reasonable doubt that a very massive cluster sat at the gravitational center of the flow. The optical identification and characterization of the Norma cluster required pushing through the zone of avoidance from a different angle. René Kraan-Korteweg, working initially at the University of Groningen in the Netherlands and later at the University of Cape Town, developed expertise in conducting deep optical galaxy searches at low galactic latitudes, in the regions where the dust extinction was severe but not total. Her approach combined wide-field photographic imaging with careful analysis to identify faint, reddened galaxies that other surveys had missed, followed by spectroscopic observations to measure redshifts and confirm physical associations. Through these surveys in the 1990s and 2000s, Kraan-Korteweg and her collaborators cataloged hundreds of previously unknown galaxies in the direction of the Great Attractor, building up a detailed picture of the galaxy population associated with the Norma cluster and the extended concentration of mass surrounding it. Their work, combined with the X-ray and near-infrared observations, established the Norma cluster as one of the most massive and structurally complex clusters in the nearby universe. The Norma cluster is extraordinary in multiple respects. Its estimated total mass, including the dark matter halo, is on the order of 10 to the 15th power solar masses, 1 quadrillion solar masses. The hot intracluster gas temperature, around 5 to 6 kiloelectron volts, is consistent with this mass through the virial theorem relationship between temperature and mass for galaxy clusters in dynamical equilibrium. The cluster shows evidence of ongoing dynamical activity, with multiple subclusters in various stages of merging and a complex X-ray morphology indicating it is not yet fully relaxed. One of the most visually striking features associated with the Norma cluster is the galaxy ESO 137-001, now famous as one of the most dramatic examples of ram pressure stripping in the nearby universe. This spiral galaxy is falling through the dense hot gas of the Norma cluster at high velocity, and the cluster medium is stripping its interstellar gas away like a hand sweeping through fog. The stripped gas forms a spectacular tail extending several hundreds of thousands of light-years behind the galaxy in X-rays and in optical emission lines. Hubble Space Telescope images and Chandra X-ray observations of this tail have revealed active star formation occurring in the stripped gas, far from the galaxy itself, a phenomenon that was unexpected and has sparked considerable theoretical interest. The jellyfish galaxy, as such objects are sometimes called, is a direct consequence of the dynamic and violent environment within the Norma cluster, testimony to the extreme conditions at the gravitational center of Laniakea. Despite all of its mass and gravitational influence, the Norma cluster cannot by itself account for the full peculiar velocity of the Milky Way and the local group. Various careful analyses over the years, using different observational data sets and different modeling approaches, have consistently found that the Great Attractor region, centered on the Norma cluster, contributes perhaps a third to a half of the observed 627 kilometers per second peculiar velocity. The remaining motion must be explained by mass concentrations farther away, operating through their long-range gravitational influence integrated over cosmic time. Moreover, the Great Attractor region itself is not at rest. Measurements of the peculiar velocities of galaxy clusters in the Great Attractor zone reveal that they too are moving in the same general direction as the local group, toward the more distant part of the southern sky where the Shapley supercluster sits. The Great Attractor is not the bottom of the gravitational valley. It is a slope on the side of a much larger mountain, and the mountain's summit, in terms of gravitational potential, lies hundreds of millions of light-years beyond the Norma cluster. Before following the trail to Shapley, it is worth pausing to understand why the zone of avoidance problem persists even today, and why the Great Attractor region remains incompletely characterized despite decades of multi-wavelength study. The zone of avoidance covers approximately 20% of the total sky, and within it, the level of obscuration varies enormously. At the lowest galactic latitudes, within perhaps 2 to 5 degrees of the exact galactic equator, the dust column is so thick that even near-infrared surveys struggle to see through it. In these directions, the universe behind the galactic plane is effectively unobservable with any currently existing technology. The density enhancements in these directions, whatever structures exist behind the thickest parts of the galactic disk, are known only indirectly from the dynamics of structures at the edges of the obscured zone. At intermediate latitudes, 5 to 15 degrees above or below the plane, the extinction is severe but not total, and careful multi-wavelength surveys have identified thousands of hidden galaxies. These form the basis for the extended characterization of the Great Attractor region that has been built up over the past 3 decades. The practical consequence is that our knowledge of the mass distribution in the most dynamically important direction in our cosmic neighborhood will always have gaps. The zone of avoidance is a fundamental limitation imposed by our position inside the Milky Way, and while future surveys using increasingly sensitive instruments at longer wavelengths will progressively reduce those gaps, they cannot be eliminated entirely. The architecture of the cosmos around us must always be partly inferred, rather than directly observed, a constraint that is built into our location in the universe and cannot be overcome by any instrument we could realistically build. Part 4. Gravity's Long Arm. The physics behind cosmic flows. One of the questions that any careful person asks when first encountering the story of the Great Attractor and the Shapley supercluster is, how can a structure hundreds of millions of light-years away exert a meaningful gravitational pull on the Milky Way? Newton's law of gravity states that the gravitational force between two objects falls off as the inverse square of the distance. Double the distance, the force becomes 1/4. Triple it, 1/9. At the distances of the Shapley supercluster, 650 million light-years, this inverse square law would seem to reduce the gravitational force to something utterly negligible. This is a reasonable thing to wonder, and the resolution of the apparent paradox is one of the most important conceptual keys to understanding large-scale structure cosmology. The gravitational force between the Milky Way and the Shapley supercluster at any given instant is indeed tiny. It is far too small to measure directly, far too small to produce any detectable effect in any single observation. But the force has not been acting for a single instant. It has been acting for the entire age of cosmic structure formation, which is most of the 13.8 billion year age of the universe. And a tiny force applied continuously for billions of years accumulates into a substantial impulse, which translates into a substantial velocity. The mathematical relationship is straightforward. Force equals mass times acceleration. So, a given gravitational force produces a given acceleration on the Milky Way's center of mass. Velocity equals acceleration multiplied by time. A very small acceleration multiplied by a very large time gives a substantial velocity. The peculiar velocity of 627 kilometers per second that we measure for the Milky Way today is the result of billions of years of gravitational acceleration by all the surrounding mass concentrations. The Shapley supercluster has been pulling on the Milky Way for approximately 10 billion years, since the large-scale structure began developing in earnest. Over that time, even a tiny average acceleration in the direction of Shapley accumulates into hundreds of kilometers per second. This perspective fundamentally reframes how peculiar velocities should be understood. A peculiar velocity is not a snapshot of an instantaneous gravitational force. It is a historical record, a compressed summary of the cumulative gravitational influence that a galaxy has experienced over its entire cosmic history. When you measure the peculiar velocity vector of the Milky Way, the direction and magnitude of that vector, you are reading out the net gravitational impulse the galaxy has received from all the mass concentrations in its surrounding volume, integrated over billions of years of cosmic time. This has profound implications for what peculiar velocity surveys tell us about the universe. Because peculiar velocities encode the cumulative gravitational history of a galaxy, they respond to all the mass in the surrounding universe. Not just the visible matter, but the invisible dark matter as well. The gravitational force that drives peculiar velocities comes from the total mass distribution, which is dominated by dark matter. Peculiar velocity surveys therefore provide a window onto the dark matter distribution that is unavailable through any other observational technique. When Tully and his collaborators built their Cosmic Flows catalogs of galaxy peculiar velocities, they were not just measuring motions. They were, in effect, mapping the dark matter distribution of the nearby universe, using the motions of visible galaxies as tracers of the invisible gravitational field. Dark matter is central to this story in a way that cannot be overstated. It constitutes approximately 27% of the total mass energy content of the universe, compared to the roughly 5% that is ordinary visible matter. The stars, gas, and dust that make up everything we can see or detect through electromagnetic radiation represent only a small fraction of the total material content of the cosmos. The remaining 27%, the dark matter, interacts only through gravity. It emits no light, absorbs no light, does not participate in electromagnetic interactions at all. We know it exists because of its gravitational effects on the rotation curves of galaxies, on the dynamics of galaxy clusters, on the large-scale structure of the cosmic web, and on the peculiar velocities of galaxies, including our own. Dark matter halos surround individual galaxies, galaxy groups, galaxy clusters, and superclusters. The dark matter halo of the Milky Way extends tens of thousands of light-years above and below the visible disk. The dark matter halo of the Norma cluster extends far beyond its visible galaxy population. The dark matter framework of Laniakea defines the gravitational basin within which the visible galaxies flow. When we talk about the mass of the Great Attractor, the mass of the Shapley supercluster, the mass budget of Laniakea, we are talking primarily about dark matter. The visible matter is a minority component, a luminous indicator of where the dark mass is concentrated. This matters for the numbers. The estimated mass of the Shapley supercluster, 10 million billion solar masses, is a mass that includes a much larger dark matter component than visible component. The cluster gas and stars that X-ray and optical telescopes detect represent perhaps 10 to 20% of the total mass. The dark matter halo surrounding the entire supercluster makes up the remaining 80 to 90%. This dark matter halo extends farther than the visible galaxy distribution and exerts gravitational influence over a larger volume. When we say the Shapley supercluster is pulling on the Milky Way, we are primarily describing the gravitational influence of this dark matter component, which makes the visible supercluster only its most compact and luminous part. The role of dark energy introduces a competing influence at large scales that is equally important to understanding the dynamics. Dark energy, which constitutes approximately 68% of the total energy content of the universe, behaves like a property of empty space itself, a constant energy density that produces a repulsive effect on the expansion of the universe. It is the driver of the accelerating expansion discovered in 1998, and its effect on cosmic structure is to set a characteristic scale above which gravitational clustering becomes ineffective. Below this characteristic scale, roughly a few 100 million light-years in the present-day universe, gravity between concentrations of matter is strong enough to overcome the dark energy-driven expansion, and structures can remain gravitationally bound, accumulating mass and holding together against the universal dispersal. Above this scale, the accelerating expansion separates structures faster than gravity can draw them together, and they become, in a dynamically meaningful sense, permanently isolated from each other. For the Milky Way's peculiar motion, dark energy means that the journey toward the Great Attractor and the Shapley supercluster is ultimately futile. We are moving toward them, yes, but the space between us and them is expanding at a rate that more than compensates for our approach. The recession velocity of Shapley from us, due to the Hubble expansion at its distance of 650 million light-years, is roughly 45,000 kilometers per second at current estimates of the Hubble constant. Our peculiar motion toward Shapley is 627 kilometers per second. We are approaching at 627 kilometers per second, while Shapley recedes from us at roughly 70 times that rate. The gap between us and Shapley is widening, not narrowing, and will continue to widen. But this does not mean the gravitational flow is irrelevant. It means that the flow represents something about the history of the universe, about the distribution of mass and the initial conditions, rather than about a physical convergence that will eventually occur. The peculiar velocities are real and substantial, encoded in the motions of hundreds of thousands of galaxies across our cosmic neighborhood. They reflect the true gravitational landscape. They simply will not, in a universe dominated by dark energy, lead to the physical assembly of the structures whose gravity drives them. The cosmic web within which we are embedded is itself evolving. Over cosmic time, dark energy progressively thins the filaments, empties the voids further, and concentrates mass into the nodes. The most massive nodes, including the Shapley supercluster, will continue to grow as matter accretes along the remaining filaments. But the connections between widely separated nodes will weaken as the accelerating expansion stretches the filaments and reduces the flows along them. Eventually, in a future so distant it makes the current age of the universe seem brief, the cosmic web will dissolve into isolated gravitational islands, separated by ever-expanding voids. The Milky Way, or what it will have become by then, will find itself in a universe increasingly devoid of the large-scale structure that currently gives our cosmic neighborhood its character. This is the context within which the Milky Way's peculiar velocity must be understood. It is a river that is real today, that has been real for billions of years, and that will remain real for billions more. But it is a river with no physical destination, a current running through a landscape that will eventually evaporate. Part 5. Laniakea, we finally found out where we live. On September 3, 2014, the journal Nature published a paper that gave the Milky Way a new address, not a minor refinement or a correction to existing knowledge. A completely new address, describing a structure that had not been clearly defined before, in a framework that recast our understanding of what a supercluster is and how cosmic boundaries should be drawn. The paper was titled The Laniakea Supercluster of Galaxies. Its authors were R. Brent Tully, Helene Courtois, Yehuda Hoffman, and Daniel Pomered. And its core insight was so elegantly simple that it seems, in retrospect, like the kind of thing that should have been done decades earlier, except that doing it required a dataset that did not exist until very recently. Before this paper, the Milky Way's cosmic address included the Virgo supercluster as the largest scale structure to which it belonged. The Virgo supercluster, also called the local supercluster, is a flattened collection of galaxy groups and clusters centered on the Virgo cluster, which itself lies roughly 53 million light-years from the Milky Way. The Virgo supercluster had been characterized as having a diameter of roughly 110 million light-year and containing on the order of 100 to 200 individual galaxies and several dozen galaxy groups and clusters. It was not a particularly precisely defined structure, and its boundaries were somewhat contested in the literature, but it served as the standard description of our cosmic supercluster neighborhood. Tully's team replaced this with something dramatically larger. Their key conceptual move was to redefine what a supercluster means. Traditional supercluster definitions were based on the spatial proximity of galaxies and galaxy clusters, structures where galaxies happen to be clustered more densely than average in a certain region of space. This definition has a fundamental problem. It depends on the smoothing scale you choose and the density threshold you apply, which means different researchers using different methods end up with different answers about where supercluster boundaries lie and which galaxies belong to which supercluster. Tully's alternative definition was based not on positions but on flows. A supercluster, in their framework, is a gravitational basin, a volume of space in which all the peculiar velocity flows are directed inward toward a common center, the same way all the water in a drainage basin flows toward the same river system. The boundary of a supercluster is the watershed surface, the three-dimensional surface in space where the flows diverge, where galaxies on one side of the surface are heading toward one gravitational center, and galaxies on the other side are heading toward a different one. This watershed definition has a crucial advantage over the traditional position-based definition. It is unambiguous. Given a sufficiently detailed map of galaxy peculiar velocities, you can compute the flow field, trace it to convergence points, and identify the watershed surfaces separating different basins. The result is a definition that has a clear physical meaning, that can be computed from observations without arbitrary choices of smoothing or density thresholds, and that correctly identifies which structures belong together gravitationally. To apply this definition, you need a comprehensive and precise map of galaxy peculiar velocities. This was provided by the Cosmic Flows 2 catalog, assembled by Tully's group using a combination of the Tully-Fisher relation for spiral galaxies, the fundamental plane for ellipticals, surface brightness fluctuations, type 1a supernovae distances, and several other methods. Cosmic Flows 2 contain distance and peculiar velocity measurements for over 8,100 galaxies spread across the sky within a few hundred million light-years. This was the most extensive, most carefully constructed catalog of galaxy peculiar velocities that existed at the time. From this velocity field, Tully's team computed what they called the velocity flow in the gravitational basin. They traced the trajectories of galaxies if they were to follow the current velocity field forward in time, asking where each galaxy's flow line would ultimately lead, which gravitational center it would converge on. They then identified the surfaces where the flow lines diverged, the watershed ridges between different basins. Within the watershed surface surrounding the basin containing the Milky Way, they found a structure far larger than anything previously described as our home supercluster. The structure they found and named Laniakea extends over more than 520 million light-years in its largest dimension. To put this number in context, the Virgo supercluster previously regarded as our home has a diameter of roughly 110 million light-years. Laniakea is nearly 5 times larger in diameter and roughly 100 times larger in volume. It contains approximately 100,000 large galaxies, of which the Milky Way is one, all sharing the same gravitational basin, all flowing toward the same center. Its total mass has been estimated at approximately 100 quadrillion solar masses, or 10 to the 17th power solar masses. Within Laniakea, the Milky Way sits near one edge, close to the watershed boundary with the neighboring Perseus-Pisces supercluster. We are not in the center of our home supercluster. We are in the outskirts, far from the gravitational focus. The center of Laniakea, the point toward which all the internal flows converge, the bottom of the gravitational basin, is the Great Attractor region. The Great Attractor, which for decades had been described as a mysterious gravitational anomaly, turned out to be the gravitational heart of home. The naming of the structure, Laniakea, was proposed in consultation with Nawaa Napoleon, a professor of Hawaiian language and culture at Kapiolani Community College in Hawaii. The name combines the Hawaiian words Lani, meaning heaven, and Akea, meaning spacious or immeasurable. The choice honored the Hawaiian tradition and the Mauna Kea Observatory, whose observations had contributed substantially to the Cosmic Flows catalog. It also simply fit. Immeasurable heaven, a supercluster so vast that human language had to reach for the infinite to find words adequate to it. The visualization created by Daniel Pomered and released alongside the paper, became one of the most widely circulated astronomical images of 2014. It showed, in 3 dimensions, the flow lines of galaxy peculiar velocities within Laniakea as white streamlines converging from all directions toward the Great Attractor. Beyond the supercluster boundary, dark blue streamlines diverged toward neighboring basins. The Milky Way appeared as a small labeled point near one edge of the structure, embedded in the vast flowing landscape, clearly and unmistakably part of something that dwarfed anything previously recognized as our cosmic neighborhood. The paper prompted an immediate reassessment of the Milky Way's cosmic address. The correct answer to "what supercluster does the Milky Way belong to?" changed from the Virgo supercluster to Laniakea in a single publication. This kind of revision to a basic fact about our place in the cosmos is remarkable for how rarely it happens in mature sciences, and it underscores how much was still unknown about the large-scale structure of our neighborhood as recently as a decade ago. But even as astronomers were absorbing the implications of Laniakea, the next question was already being asked. Laniakea is itself moving. The entire supercluster has a bulk peculiar velocity directed toward the same general part of the southern sky where the Great Attractor sits. This means the Great Attractor is not the ultimate gravitational destination of the flow. It is a stepping stone on the way to something still larger and more distant. And the most obvious candidate for that larger attractor, given the direction of the flow and the known mass concentrations in that part of the universe, was the Shapley supercluster. Part 6. The Shapley supercluster, the most massive structure in our billion-light-year neighborhood. In the summer of 1930, the American astronomer Harlow Shapley was engaged in the systematic cataloging of galaxies across the sky, part of a broader program to understand the distribution of galaxies at the largest scales then accessible to observation. This was early work in what would eventually become the project of mapping the large-scale structure of the universe, and it was conducted with the modest tools available in that era: photographic plates, large but not enormous telescopes, and the patience required to count and catalog faint smudges of light by hand. In the direction of the constellation Centaurus, at what could be loosely estimated as a very large distance, Shapley noticed an unusual concentration of galaxies. The number of galaxy images per square degree of sky was dramatically elevated compared to the surrounding fields and compared to other regions at similar distances in other parts of the sky. He described it as a remarkable concentration, included it in his survey data, and moved on. In 1930, there were no tools to measure how far away the concentration was, no framework for understanding what such a concentration might mean dynamically, and no way to connect it to the motion of the local group, because the concept of large-scale peculiar velocities had not yet been formulated. Shapley made a note in a notebook, added data to a catalog, and the observation waited for the world to catch up to it. It took the world about 60 years. What Shapley had found is now called the Shapley supercluster, or the Shapley concentration, and it is one of the most extraordinary objects in the observable universe. Not in the whole universe, which extends far beyond what we can see. But within roughly 1 billion light-years of the Milky Way, the Shapley supercluster is the dominant concentration of matter, the largest and most massive known structure, the king of our particular corner of the cosmos. The Shapley supercluster sits approximately 650 million light-years away, in roughly the same direction as the Great Attractor, but at nearly 3 times the distance. Its extent on the sky is substantial, spanning tens of degrees across even from 650 million light-years away, an indication of how physically large it is. Estimates of its total size range from roughly 200 million light-years for the compact central core to perhaps 600 million light-years for the full extent of the surrounding structure and its connecting filaments, depending on where you draw the boundary. Its core is dominated by a dense collection of rich galaxy clusters. Abell 3558, also called the Shapley 8 cluster, is the central and most massive structure, sitting at the heart of the Shapley supercluster complex. It is classified as one of the richest clusters in the Abell catalog, meaning it contains an exceptionally high number of bright galaxies per unit area. Nearby are Abell 3562 and Abell 3556, 2 more rich clusters connected to A3558 by bridges of galaxies and diffuse gas, and farther out within the supercluster core are Abell 3559, Abell 3560, and numerous additional clusters and groups, all bound together by their mutual gravity into a single enormous complex. ESA's Planck satellite provided one of the most comprehensive recent assessments of the Shapley supercluster's properties. Planck could detect the Shapley supercluster not just as a concentration of galaxies visible in optical images, but as a feature in the cosmic microwave background through the thermal Sunyaev-Zeldovich effect. The hot gas pervading the clusters in the Shapley supercluster scatters and distorts the CMB photons passing through it in a characteristic way, producing a signal in the Planck maps that can be used to measure the total mass of the hot gas and, by extension, the total gravitational mass of the system. These measurements confirm that the Shapley supercluster is the most massive known structure within approximately 1 billion light-years of the Milky Way. The aggregate mass estimate for the Shapley supercluster is approximately 10 million billion solar masses, written as 10 to the 16th power in solar mass units, sometimes also expressed as 10 quadrillion solar masses. The number is so large that it essentially loses meaning without careful contextualization. The Milky Way's total mass, including dark matter, is approximately 1 trillion solar masses. The Shapley supercluster has the equivalent mass of 10 million Milky Ways. If you could somehow duplicate the entire mass of our galaxy 10 million times and pack it into the volume of the Shapley supercluster, you would have reproduced its total gravitational influence. It is a number that exceeds the scope of any everyday comparison. The role of the Shapley supercluster in driving the peculiar velocities of the nearby universe, including the motion of the Milky Way, was recognized gradually through the late 1990s and early 2000s. Early analyses of the Seven Samurai data had focused primarily on the Great Attractor region, which was closer and therefore more obviously connected to the observed flows. The Shapley supercluster, at 3 times the distance, was seen as a background feature rather than a primary driver. But as surveys of the broader mass distribution became more complete, and as models of the relationship between mass distribution and peculiar velocities became more sophisticated, it became clear that Shapley's contribution had been systematically underestimated. The decisive evidence came from the CIZA survey, conducted by Dale Kochevsky, working with Harold Ebeling at the University of Hawaii. The clusters in the zone of avoidance survey used rosette X-ray data to identify galaxy clusters across the full sky, including the zone of avoidance, and build a comprehensive mass inventory of the structures potentially driving the local group's peculiar motion. Kochevsky's analysis found that the Great Attractor region, including the Norma cluster and surrounding structures, contained significantly less mass than some earlier estimates had suggested. The Great Attractor was not as great as its name implied, at least not in its own right. Meanwhile, the Shapley supercluster, at its greater distance, contained 4 times the mass visible in the Great Attractor region and exerted a gravitational influence that, when combined with the Great Attractor's contribution, brought the predicted peculiar velocity of the local group into much closer agreement with the observed value. The conclusion was clear. Both the Great Attractor, at 220 million light-years, and the Shapley supercluster, at 650 million light-years, are significant contributors to the Milky Way's peculiar velocity, with Shapley contributing as much or more despite its greater distance because of its much larger mass. The dominant long-range gravitational influence on the Milky Way is the most massive structure in our billion light-year neighborhood, a supercluster that Harlow Shapley noticed as a photographic density enhancement in 1930, and that we are still in the process of fully characterizing nearly a century later. The Shapley supercluster is not a static, finished object. It is dynamically active, still in the process of assembling itself through the hierarchical merging of subclusters and the continued accretion of infalling material from surrounding filaments. The central clusters show high-velocity dispersions and complex X-ray morphologies indicating ongoing dynamical interactions. Multiple groups of galaxies are falling into the cluster complex along the filaments connecting Shapley to the surrounding cosmic web, adding to its mass on cosmological timescales. Shapley is the dominant node of the web in our neighborhood, and it is still growing, still accumulating the matter that its gravity is drawing in from the surrounding volume. The gravitational influence of Shapley extends far beyond its visible boundary. The dark matter halo surrounding the entire supercluster complex reaches out into the surrounding intergalactic space, gradually weakening with distance, but never entirely vanishing. At the distance of the Milky Way, 650 million light-years, the gravitational force from Shapley at any given instant is tiny, but it has been acting continuously for the age of cosmic structure formation and the cumulative impulse it has imparted to the local group adds up to a substantial fraction of our observed peculiar velocity. The story of the Shapley supercluster is in some ways the most remarkable part of the entire investigation of what pulls the Milky Way across the universe. It is a structure whose existence was noticed before anyone had the tools to understand it, whose role in the dynamics of our cosmic neighborhood was suspected before anyone could confirm it, and whose full characterization is still ongoing as surveys improve and our ability to probe behind the zone of avoidance deepens. It represents exactly the kind of discovery that science produces when patience, technology, and theoretical frameworks converge on a problem that has been waiting for all three. Part 7. The Dipole Repeller. When emptiness becomes a force. In the years following the 2014 Laniakea paper, the picture of what drives the Milky Way's peculiar motion seemed reasonably well established. The great attractor at the center of Laniakea, pulling the local group toward the southern sky, the Shapley supercluster farther behind it, pulling both the local group and the great attractor region with its enormous gravitational mass. Together, these two attractors, one near and one far, seem to provide a reasonable accounting of the observed 627 kilometers per second directed toward Centaurus. But there was always something slightly unsatisfying about the purely attractor-based picture. For years, cosmologists had understood in principle that cosmic voids should be contributing an effective push to the peculiar velocities of nearby galaxies, in addition to the pull of the overdense structures. The physics was clear. A large void in one direction creates a gravitational imbalance that accelerates nearby matter away from the void and toward the denser structures on the other side. The absence of mass is, in terms of its effect on motions relative to the Hubble flow, operationally equivalent to a repulsion. The question was whether there was a large, clearly identifiable void in roughly the opposite direction from Shapley, behind the Milky Way, that was contributing a significant push to our peculiar velocity. If so, accounting for it would both improve the model of our motion and change the conceptual picture from being pulled from one side to being pulled from one side and pushed from the other. For several years, the evidence for such a void was suggestive but not conclusive. The galaxy distribution in the anti-Shapley direction appeared somewhat underdense, but the data were not sufficient to clearly identify a specific large supervoid with a well-characterized mass deficit. Hints appeared in analyses of X-ray cluster distributions, where a deficiency of clusters was noted in that part of the sky, but the statistical significance was not strong enough to make a definitive claim. The resolution came on January 30th, 2017, when Yehuda Hoffman of the Hebrew University of Jerusalem, together with Daniel Pomered, Brent Tully, and Hélène Courtois, published a paper in Nature Astronomy titled The Dipole Repeller. Using the Cosmic Flow's 3 peculiar velocity catalog, which substantially improved on the Cosmic Flow's 2 data used for the Laniakea analysis by including more galaxies at greater distances and with refined distance measurements, the team reconstructed the 3-dimensional gravitational potential field of the nearby universe with greater precision than had been possible before. This reconstruction identified not only the attractors, the gravitational potential wells corresponding to overdense structures, but also the repellers, the gravitational potential hills corresponding to underdense structures. The most prominent repeller in the reconstructed field was a large, clearly defined underdensity located in roughly the direction diametrically opposite to the Shapley concentration. They named it the dipole repeller, emphasizing that it formed one pole of a dipole system, with Shapley as the other pole, aligned with the CMB dipole direction. The dipole repeller sits approximately 600 million light-years from the Milky Way, at a distance comparable to the Shapley supercluster, but in the roughly opposite direction. It is characterized by a substantially below-average density of galaxies over a large volume, a supervoid in the parlance of large-scale structure cosmology. The few galaxies that do exist within it are sparse and scattered, with a surface density on the sky significantly below that of surrounding regions. The mass deficit, relative to the average density of the universe over that volume, is substantial enough to create a meaningful gravitational imbalance. Hoffman's team found that the combination of the Shapley attractor pulling from one side and the dipole repeller pushing from the other could explain both the direction and the magnitude of the Milky Way's peculiar velocity more accurately than the attractor-only model. Their explicit conclusion was that push and pull were of comparable importance at our location. We are not primarily being pulled toward Shapley with a minor push from a background void. We are being subjected to gravitational influences of comparable magnitude from two sides, a pull toward the most massive known structure in our billion light-year neighborhood and a push away from one of the most prominent voids. The physical mechanism of the push is worth understanding carefully because the dipole repeller does not exert an actual repulsive force in the sense of pushing matter away from it. Gravity is always attractive. What the void does is create a gravitational deficit in one direction relative to the average. Imagine being surrounded by a roughly uniform distribution of matter, with a large hole punched in one side. The matter on the intact side pulls you toward it with roughly the average force. The matter on the hole side pulls you with less than the average force, because there is less mass there. The net effect is an acceleration toward the intact side and away from the hole, relative to the Hubble flow that would exist in a uniform universe. From the perspective of peculiar velocity, relative to the Hubble flow, the void appears to repel. This is not a subtle or second-order effect. In a universe where the most prominent voids span hundreds of millions of light-years and have mass deficits corresponding to trillions of solar masses, the effective gravitational push from a large nearby void can be comparable in magnitude to the pull from a large nearby overdensity. The dipole repeller demonstrates this quantitatively for the Milky Way. The void behind us is contributing roughly as much to our peculiar velocity as the supercluster in front of us. The discovery of the dipole repeller also validated a prediction that had been made in general terms by many cosmologists over the preceding years. Numerical simulations of cosmic structure formation in standard cosmological models consistently showed that voids should be important contributors to the peculiar velocities of galaxies in their vicinities, not just small corrections to an attractor-dominated picture. The identification of a specific large void in the appropriate location behind the Milky Way confirmed that this theoretical expectation was realized in our actual cosmic neighborhood. The name dipole repeller connects to a broader feature of the CMB and the motion of the local group. The CMB dipole, the slight temperature asymmetry between the direction we are moving toward and the direction we are moving away from, is one of the most precisely measured features of the cosmic microwave background. Its amplitude corresponds to our velocity of 627 kilometers per second. Its direction defines an axis in the sky, with a warm pole in the direction of motion and a cool pole in the direction we are receding from. The Shapley attractor is near the warm pole, and the dipole repeller is near the cool pole. The two structures together define the physical causes of the CMB dipole, the attractor we are heading toward, and the void we are fleeing from. Future surveys at optical, near-infrared, and radio wavelengths were expected to directly map the sparse galaxy population within the dipole repeller void, confirming its extent and characterizing its properties in detail. The few galaxies expected to exist within the void should be identifiable in sufficiently deep surveys, providing a direct observational confirmation of the structure that the flow field reconstruction identified indirectly. This work represents an ongoing frontier of observational cosmology. Part 8. Dark Flow and the Debate That Won't Die. The combination of the Great Attractor, the Shapley supercluster, and the dipole repeller represents the current best understood picture of what drives the Milky Way's peculiar motion. But the path to this understanding was not smooth, and along the way, a more radical proposal attracted significant attention and generated a controversy that has not been entirely resolved. In 2008, Alexander Kashlinsky of NASA's Goddard Space Flight Center and colleagues Fernando Atrio Barandela, Dale Kochevsky, and Harold Ebeling published a paper in the Astrophysical Journal Letters claiming to have detected what they called a dark flow, a bulk motion of galaxy clusters across an enormous volume of space that could not be explained by any known structure within the observable universe, and that they attributed to the gravitational influence of matter beyond the cosmological horizon. The technique they used was based on the kinematic Sunyaev-Zeldovich effect, a subtle spectral distortion of the cosmic microwave background produced when the hot gas in a galaxy cluster scatters CMB photons, while the cluster is moving relative to the CMB rest frame. The scattering shifts the CMB photons in a way that reflects the cluster's velocity along the line of sight, very slightly warming the CMB in the direction the cluster is moving toward, and cooling it in the direction the cluster is moving away from. The effect is extraordinarily small for any single cluster, far below the threshold of detection, but can in principle be extracted statistically from a large catalog of clusters by averaging over many objects. Kashlinsky and colleagues developed a statistical method to extract this signal from the temperature maps produced by NASA's WMAP satellite. Using a catalog of approximately 700 X-ray galaxy clusters, they applied their method to the WMAP data and found a bulk motion signal. The clusters appeared to be moving coherently toward a region of the sky in the direction of the constellations Centaurus and Vela, broadly consistent with the direction of the known great attractor flow. This was not immediately surprising. What was surprising, and what made the dark flow claim extraordinary, was the distance behavior of the signal. For a bulk flow driven by known local structures, the amplitude of the peculiar velocities should diminish with increasing cluster distance, because the gravitational influence of structures like Shapley and the Great Attractor falls off with distance. Nearby clusters should show large peculiar velocities. Distant clusters should show small ones. But when Kashlinsky's team sorted their cluster catalog by distance and analyzed each bin separately, the bulk flow signal did not diminish at large distances. It appeared to persist with roughly the same amplitude out to the deepest distance bins, corresponding to distances of over 2 billion light-years. This was, if real, a dramatic violation of expectations. No structure within the observable universe could maintain constant gravitational influence across distances of 2 billion light-years. The only explanation that Kashlinsky's team could offer was that the clusters were responding to the gravitational influence of matter outside the cosmological horizon, beyond the edge of the observable universe. Matter that was pushed there by inflation in the earliest moments of the universe, but whose pre-inflationary gravitational imprint could still be influencing the distribution of matter within the observable region. The observable universe has a radius of approximately 46 billion light-years, defined as the distance light has had time to travel since the Big Bang, accounting for the expansion of space. The total universe almost certainly extends much farther, inflated to an enormous size during the exponential expansion period in the universe's first tiny fraction of a second. Matter beyond the cosmological horizon has had no causal contact with our observable region since inflation ended, but the gravitational effects of the pre-inflationary state could, in some theoretical frameworks, leave imprints that manifest as preferred directions or bulk flows within the observable region. The response from the cosmological community was immediate, substantial, and largely skeptical. The kinematic Sunyaev-Zeldovich effect is one of the most difficult signals to extract from CMB data, requiring exquisite control of numerous systematic effects. The thermal Sunyaev-Zeldovich effect, which is caused by the hot gas temperature rather than cluster motion and is much larger than the kinematic version, must be accurately subtracted. Foreground emission from the Milky Way must be removed. Instrumental effects in the WMAP data must be characterized and corrected. Each of these steps involves choices and assumptions that can affect the extracted signal at the level of the claimed dark flow amplitude. Multiple independent teams attempted to reproduce the dark flow result using their own analyses of WMAP data, different cluster catalogs, and different statistical methods. The results were inconsistent. Some analyses found hints of a bulk flow in roughly the expected direction. Others found no significant signal or a signal much weaker than Kashlinsky's claim. The inconsistency of the reproductions raised doubts about the robustness of the original result. The most definitive test came from the Planck satellite mission. ESA's Planck, launched in 2009 and operating until 2013, produced the most precise and comprehensive CMB maps ever made, with lower noise levels, better control of systematic effects, and improved frequency coverage compared to WMAP. The Planck collaboration applied the kinematic Sunyaev-Zeldovich technique to their data using multiple cluster catalogs, including those used by Kashlinsky. The results, published in a series of Planck collaboration papers, found no significant evidence for a dark flow at the amplitude claimed by Kashlinsky. The bulk flow in the nearby universe appeared consistent with predictions from the standard cosmological model, driven by the known distribution of matter within the observable universe. Kashlinsky and his collaborators responded to the Planck analyses in subsequent publications, arguing that differences in methodology, cluster selection, and the treatment of systematic effects could account for the discrepancy, and that their signal remained present in the data when their specific analysis choices were applied. The debate continued for several years, with neither side fully persuading the other. As things stand in the mid-2020s, the mainstream view holds that there is no convincing evidence for a dark flow at the amplitude originally claimed, and that the peculiar motions of the nearby universe are adequately explained by known structures within the observable universe. The Shapley supercluster and the dipole repeller, combined with the Great Attractor region and the full three-dimensional density field of the nearby cosmic web, appear to account for the observed bulk flows without requiring any contribution from beyond the horizon. But the question that the dark flow controversy raised remains scientifically interesting at the conceptual level. Can anything beyond the cosmological horizon influence what happens within it? In the strict framework of general relativity with standard initial conditions, the answer is no. Gravity propagates at the speed of light, and no signal from beyond the horizon has had time to reach us. But the question becomes subtler when you consider that inflation connected regions that are now beyond each other's horizons, and that the initial conditions of the observable universe were set in a context where those connections existed. Whether those pre-inflationary connections left observationally accessible imprints remains an open theoretical question. Part 9. The Cosmic Web, the architecture that explains everything. The Great Attractor, Laniakea, the Shapley supercluster, the dipole repeller, all of these specific features of our cosmic neighborhood make sense only within the context of the larger framework that produced them. The cosmic web, the large-scale structure of the universe that grew from the initial conditions of the Big Bang and continues to organize the distribution of matter and the flows of galaxies across the full range of observable scales. The cosmic web consists of 4 types of region that together partition all of space. The densest and most massive are the clusters and superclusters, the nodes of the web at the intersections of multiple filaments, places where gravity has concentrated enormous quantities of matter into relatively compact volumes and where the most luminous and energetic objects in the universe, the giant elliptical galaxies and the quasars powered by supermassive black holes, predominantly reside. Next are the filaments, the thread-like bridges connecting the nodes, channels of dark matter and gas along which galaxies flow toward the denser regions. Then there are the walls, broad sheet-like structures that form the boundaries between large voids, somewhat less concentrated than filaments, but clearly identifiable as overdense relative to the surrounding emptiness. And finally, dominating by volume, are the voids, vast regions nearly empty of galaxies and dark matter, from which matter has been streaming outward along the filaments for billions of years. This architecture grew from almost nothing. In the first moments after the Big Bang, the universe was an almost perfectly uniform plasma of fundamental particles and radiation. The word almost is crucial because the physics of the very early universe ensured that perfect uniformity was impossible. Quantum mechanics, the framework governing the behavior of matter at the smallest scales, imposes unavoidable random fluctuations on all physical fields. In the inflationary epoch, the period of extraordinarily rapid exponential expansion that cosmologists believe occurred in the first tiny fraction of a second, these quantum fluctuations were stretched to macroscopic scales and frozen in as density perturbations in the early universe. These perturbations are tiny, roughly 1 part in 100,000 in amplitude, meaning that overdense regions were about 0.001% denser than the average and underdense regions were about 0.001% less dense. But they were spatially correlated in a specific way, with a spectrum of fluctuations on different scales that has been precisely measured by CMB experiments, and that matches the predictions of inflationary models. This specific pattern, set down in the first fractions of a second, is the seed from which the entire cosmic web grew over 13.8 billion years of gravitational amplification. Gravity is the engine of amplification. The slightly denser regions attracted slightly more matter, became slightly denser still, attracted yet more matter. The slightly underdense regions lost mass to their surroundings, becoming emptier, attracting less matter, becoming emptier still. Over time, the contrast between overdense and underdense regions grew from 1 part in 100,000 to the dramatic extremes we observe today, where the densest cluster cores are millions of times denser than the average and the emptiest void. Interiors are a small fraction of the average. The cosmic web grew from quantum whispers to cosmic shouts over the age of the universe. Dark matter was essential to this amplification process. and its role cannot be overstated. Ordinary matter in the early universe was coupled to the radiation field through electromagnetic interactions. The photons and baryons, the ordinary protons and electrons, formed a tightly coupled plasma in which the radiation pressure resisted gravitational collapse on scales smaller than a characteristic length called the Jeans length, which in the hot early universe was substantial. This radiation pressure prevented ordinary matter from beginning to clump significantly until the epoch of recombination, roughly 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form and the coupling between matter and radiation ended. Dark matter, interacting only through gravity, was not subject to this constraint. It began clumping under its own self-gravity as soon as the primordial fluctuations provided seeds for it to collect around. By the time recombination occurred and ordinary matter was free to clump, the dark matter had already built a scaffolding of overdense regions and connecting bridges. The ordinary matter fell into this pre-existing dark matter scaffolding almost immediately, tracing the structure that the dark matter had already established. This is why the large-scale structure of the universe, as traced by the visible galaxies, so closely mirrors the expected distribution of dark matter. The galaxies are luminous markers of the dark matter architecture. Computer simulations of this process, beginning from CMB-calibrated initial conditions and evolving forward under the combined influences of gravity, dark matter dynamics, dark energy, gas physics, and the feedback from star formation and supermassive black holes, produce universes that look strikingly like the real one. The Millennium Simulation, one of the landmark computations in cosmological history, ran in 2005 at the Max Planck Institute for Astrophysics under the leadership of Volker Springel and collaborators. It tracked 10 billion dark matter particles in a cubic volume about 2 billion light-years on a side over the full age of the universe. The resulting structure, when visualized in 3 dimensions, shows exactly the web-like architecture of filaments, nodes, and voids that galaxy surveys reveal. The statistical properties of the simulated web, how clusters are distributed, how voids are shaped, how the peculiar velocity field relates to the density field, match observations of the real universe across a wide range of scales. The Great Attractor, Laniakea, and the Shapley supercluster are the dominant nodes of the cosmic web in our local volume. They represent the largest mass concentrations that gravity has assembled from the initial conditions within roughly a billion light-years of the Milky Way. The dipole repeller represents one of the prominent voids, a region where the initial conditions happen to be slightly underdense, and which has been evacuating itself over the age of the universe as matter streams away along the surrounding filaments. The Milky Way's peculiar velocity is, from this perspective, unremarkable. It is the standard behavior of a galaxy embedded in a specific location within the cosmic web, responding to the gravitational field of all the surrounding structure through the cumulative effect of billions of years of acceleration. Every galaxy in the observable universe has a peculiar velocity for exactly the same reason. The specific numbers for the Milky Way, the specific direction and magnitude, are determined by the specific arrangement of overdensities and underdensities in our particular neighborhood, but the phenomenon is universal and expected. What makes the story of mapping the Milky Way's peculiar motion scientifically interesting is not the peculiarity of the motion itself, but what the investigation has revealed about the architecture of our cosmic neighborhood. The Great Attractor, Laniakea, Shapley, the dipole repeller. Each of these identifications was a major scientific discovery, revealing features of the large-scale structure of the universe that were previously unknown or poorly characterized. The investigation of what pulls the Milky Way across the universe turned out to be, simultaneously, the project of mapping our position within the cosmic web and understanding the gravitational architecture of the billion light-year volume around us. That project is not finished. The zone of avoidance still hides structures that have not been fully mapped. The South Pole Wall, a massive filamentary structure discovered in 2020 using the Cosmic Flows 3 catalog, stretches roughly 1.4 billion light-years and may be connected to the Shapley region in ways still being characterized. The Vela supercluster, identified in 2017 by a team led by René Cron-Cordaweg using a survey that penetrated the zone of avoidance, is a significant mass concentration behind the galactic plane, whose contribution to our peculiar motion is still being quantified. The Cosmic Flows 4 catalog, published in 2023, has already generated new analyses suggesting that Laniakea may be a tributary of a still larger structure centered on Shapley. The map continues to be refined. Part 10. The destination we will never reach: dark energy and cosmic fate. The Milky Way has been moving toward the Great Attractor and ultimately toward the Shapley supercluster for the entire age of cosmic structure formation, and it will continue to do so for the foreseeable future. But the Milky Way will not reach these destinations. The universe has mechanisms that prevent it, fundamental mechanisms built into the physics of the cosmos, and understanding them is essential to understanding what the Milky Way's cosmic journey actually means. The mechanism is dark energy and the accelerating expansion it drives. The expansion of the universe was established by Edwin Hubble's observations in 1929, which showed that distant galaxies were receding from us at velocities proportional to their distances. The interpretation, developed in the following decades, was that the universe has been expanding since the Big Bang, and that this expansion was gradually decelerating under the mutual gravitational attraction of all the matter within it. The natural expectation was that gravity would eventually slow the expansion, perhaps halt it, and possibly reverse it into a recollapse. The precise fate depended on the total density of matter in the universe relative to a critical value. In 1998, this picture was overturned by the observations of distant Type 1a supernovae. Type 1a supernovae are the explosions of white dwarf stars that exceed a critical mass through accretion from a companion, and they are calibrated standard candles because their intrinsic luminosity at peak brightness is well characterized. By comparing the intrinsic luminosity to the apparent brightness, astronomers can determine the true distance to each supernova, and by comparing that true distance to the redshift inferred distance, they can test whether the universe's expansion history matches theoretical predictions. Two independent teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt with Adam Rees, found the same unexpected result. The distant supernovae were fainter than expected. They were farther away than a decelerating or even coasting universe would predict. The universe's expansion was not slowing down. It was speeding up. This discovery, which earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics, introduced dark energy into modern cosmology. Dark energy is the name given to whatever is causing the accelerating expansion, and it behaves as though every cubic meter of empty space contains a small positive energy density that acts as a repulsive pressure. The most natural interpretation is the cosmological constant, originally proposed by Einstein in 1917 and then abandoned, now reinterpreted as a vacuum energy density inherent to empty space. Its value, as determined from observations, is extraordinarily small, on the order of 10 to the minus 29 grams per cubic centimeter, but it pervades all of space, and its cumulative effect over cosmological volumes is enormous. Dark energy constitutes approximately 68% of the total energy content of the universe. It dominates over dark matter at 27% and ordinary matter at 5%, and its effect on structure formation is to set a scale above which gravitational clustering cannot overcome the expansion. For any two structures in the universe, there is a competition between gravity, which pulls them together, and the dark energy-driven expansion, which pushes them apart. At separations below a characteristic scale that depends on the mass of the structures and the dark energy density, gravity wins and the structures can remain gravitationally bound. Above this scale, the expansion wins and the structures are permanently separated. For the Milky Way and the Shapley supercluster, separated by 650 million light-years, the expansion wins decisively. At that distance, the Hubble recession velocity is approximately 45,000 kilometers per second, while our peculiar approach velocity toward Shapley is 627 kilometers per second. The net effect is that Shapley is receding from us at roughly 44,373 kilometers per second. The space between us and Shapley is expanding, not contracting. We will never physically reach the Shapley supercluster. For the Great Attractor at 220 million light-years, the situation is less extreme, but the conclusion is the same. Our infall velocity toward the Great Attractor is also part of the 627 kilometers per second of total peculiar motion. And the Hubble recession at 220 million light-years is still far greater than any plausible peculiar velocity toward it. The accelerating expansion ensures that even the gravitational center of our own supercluster, Laniakea, is receding from us faster than we approach it. What about Laniakea itself as a structure? Is Laniakea gravitationally bound, destined eventually to merge into a single system? The answer depends on whether the internal peculiar velocities of galaxies within Laniakea are large enough to overcome the dark energy-driven expansion across the supercluster's 520 million light-year extent. Detailed analyses of the dynamics suggest that only the innermost, densest regions of Laniakea, the Great Attractor Core, and the structures within perhaps a few tens of millions of light-years of it are likely to be genuinely gravitationally bound and destined to eventually merge. The outer regions of Laniakea, including the Milky Way near its edge, are probably not gravitationally bound to the supercluster center in the sense of being destined to converge, because the dark energy-driven expansion is too powerful at these scales. The future of the Milky Way is dominated not by what happens at the galactic scale, the Great Attractor, or even Laniakea, but by the local scale, the merger with the Andromeda Galaxy, which is currently approaching at about 110 kilometers per second, and will begin a significant gravitational interaction in approximately 4 to 4.5 billion years. This merger will transform both galaxies over several billion years of close passes and gravitational interaction, eventually producing a single large elliptical galaxy from the remnants of both spirals. This merged system, containing the combined stars and dark matter of both galaxies, will continue flowing toward the Great Attractor on the same general trajectory, but the expansion of space will ensure that the destination remains perpetually out of reach. Over trillions of years, the accelerating expansion will progressively isolate gravitationally bound structures from each other. The filaments of the cosmic web will thin as the matter in them is either accreted into the cluster nodes or carried away by the expansion. Eventually, isolated gravitationally bound groups and clusters will survive as islands in an ever-expanding void, while the larger-scale structure of the web dissolves. The observable universe from within any galaxy will shrink as the most distant galaxies are carried beyond the cosmological horizon by the accelerating expansion, their light perpetually redshifted until it falls below any conceivable detection threshold. In this far future, the cosmic rivers will have dried up. The flows that today carry the Milky Way toward the Great Attractor and carry Laniakea toward Shapley will have dissipated. The structures driving the flows will still exist, internally, but the connections between them will have been severed by the expansion. The Milky Way's journey will be permanent, endless, without a rival. There is something philosophically interesting in this. The universe has motion built into it at every scale. Galaxies flow in cosmic rivers. The rivers run toward attractors. The attractors are themselves in motion toward larger attractors. But at every level, dark energy ensures that the destination is never quite reached. The journey is never complete. The river flows without arriving at the sea. The universe is a place of perpetual motion and perpetual incompletion, structured by gravity but ultimately governed by the restless expansion that carries everything apart. Part 11. What this means. Our place in the cosmic current. Everything we have covered in this video, from the faint temperature asymmetry in the cosmic microwave background that first revealed our motion, to the Seven Samurais' identification of the Great Attractor, to Tully's definition of Laniakea, to the discovery of the dipole repeller, represents a body of knowledge that did not exist 50 years ago, and that has been assembled in remarkable detail over the past 3 decades of observational cosmology. What does this picture tell us, taken as a whole? It tells us that we are not at the center of anything. We sit near the edge of our home supercluster, Laniakea, which is itself part of a larger flow toward the Shapley supercluster, which is itself a node in the cosmic web stretching across the entire observable universe. We are one data point in a field of 100 quadrillion solar masses of flowing galaxies, located near the periphery of the structure, on the outskirts of the largest gravitational basin in our billion light-year neighborhood. It tells us that the universe has a specific, identifiable architecture at the largest scales, an architecture that was determined by quantum fluctuations in the first fraction of a second of cosmic history and that has been developing and elaborating through gravitational amplification for the entire 13.8 billion year age of the cosmos. The Great Attractor is not an accident. The Shapley supercluster is not a coincidence. The dipole repeller is not random emptiness. These are the specific expected features of a universe with the particular initial conditions set down in the Big Bang, evolved under the particular laws of physics we have measured. It tells us that we are simultaneously being pulled and pushed, that our motion through the universe is the result of both an attraction toward the most massive structure in our neighborhood and an effective repulsion from a vast void in the opposite direction. The cosmic journey is not a simple one-way trip toward a gravitational destination. It is a more complex navigation through a gravitational landscape of mountains and valleys, attractors and repellers, the densest nodes and the emptiest voids of the cosmic web. It tells us that dark energy imposes a fundamental limit on the gravitational story. The flows are real, the peculiar velocities are substantial, the structures driving them are among the most massive in the observable universe. But the accelerating expansion ensures that no convergence will actually occur. We will travel toward the Great Attractor forever without arriving, pulled forward and pushed from behind, in a journey that has no physical conclusion. And it tells us something about our moment in history. The answers to the most basic questions about our cosmic address, what supercluster we live in, what is pulling our galaxy across the universe, what structures define our gravitational neighborhood, were not known in any complete form until very recently. The identification of Laniakea was in 2014. The dipole repeller was in 2017. The South Pole wall was in 2020. We are living in the era when the large-scale map of our cosmic neighborhood is being drawn for the first time, when the basic facts of our cosmic situation are being established from scratch. This makes the current moment in cosmological observation genuinely special. The Cosmic Flows 4 catalog, published in 2023, is already generating new analyses. Future surveys with instruments like the DESI spectrograph, the Rubin Observatory, and the Euclid Space Telescope will measure galaxy distances and peculiar velocities with far greater precision and far greater numbers than anything available today. The zone of avoidance will be progressively peeled back by deeper infrared and radio surveys. The structures of the local cosmic web will be mapped at higher resolution and to greater distances than is currently possible. Each of these improvements will refine the picture. Some features currently characterized only roughly will come into sharp focus. Some structures currently known only from indirect evidence will be directly mapped. And almost certainly, structures are lurking in the parts of the sky we have not yet surveyed deeply enough, or hidden behind the galactic plane, that will add new features to the map when they are eventually found. The river we are in is real, the current is measurable. The mountains and valleys of the gravitational landscape have been named. Laniakea is home. The Great Attractor is the floor of our valley. The Shapley supercluster is the dominant mountain in our view. The dipole repeller is the void at our backs. And between all of these, the Milky Way flows, carried by forces that predate the Sun and the Earth by billions of years, moving through a universe that is simultaneously structured and expanding, ordered and dissolving, pulling us forward and carrying us apart. We are perpetual travelers in a river that has no sea. And now, finally, we know the landscape through which it flows. If this exploration of the cosmic forces shaping our galaxy's journey gave you that quiet, slightly vertiginous feeling that comes from genuinely grasping the scale of the universe, like helps this content reach more people. And if you have been watching without subscribing, this is the right video to change that. New videos in this series take on topics exactly like this one, approaching the largest questions in cosmology with the patience and depth they deserve. Thank you for watching. Expanded section. Part 1. Additional depth on the invisible river. Consider for a moment what it would mean to be able to step outside the Milky Way and watch it from a great distance. Not a nearby distance, because there is no object close enough to our galaxy from which its motion through space would be apparent in a human lifetime. We would need to step to some imaginary vantage point outside the cosmological flow entirely, a God's eye view from which the entire local universe could be watched as a single scene, the way you might watch a school of fish moving through water. From that vantage point, what would you see? You would see a flattened spiral disk of stars, glowing with a pale blue-white light from its spiral arms where young, hot stars illuminate the surrounding nebulae, and with a warmer yellowish glow from the central bulge where older red and orange stars dominate. You would see dark lanes of dust tracing along the spiral arms, absorbing the light of stars behind them, giving the disk its characteristic banded appearance. Around the disk, extending above and below in a roughly spherical distribution, you would see the faint haze of the galactic halo, the globular clusters tracing their ancient orbits, and the invisible but gravitationally dominant dark matter halo that contains most of the galaxy's total mass. And all of it, every part of it, would be moving, not just rotating around its own center, though it does that too, with stars at the sun's radius completing an orbit every 225 to 250 million years, moving through space, drifting smoothly and steadily in the direction of the southern sky of the galaxy's reference frame, toward the great concentrations of matter that draw it forward. The motion would be invisible at ordinary timescales. You would need to watch for millions of years to see any perceptible displacement, and for tens of millions of years to see something you might call obvious movement. The universe is simply too large for galactic motions to be cinematically interesting on any timescale accessible to human experience. We built civilization, developed science from scratch, invented telescopes, launched satellites, all in the cosmic equivalent of a single heartbeat. But from a vast enough temporal vantage point, watching the history of the local universe compressed into a few seconds, you would see rivers, streams of galaxies flowing along the cosmic web's filaments, clusters slowly growing at the nodes as they accumulate in falling matter, voids slowly expanding and emptying as their constituent matter drains away into the surrounding structure. And within this flowing landscape, the Milky Way and its neighbors, all drifting steadily toward the gravitational basin at the center of the local supercluster, responding to the same invisible tug that has been shaping their trajectories since the structure of the cosmos first began to emerge from the primordial uniformity. This is what we mean when we say the Milky Way is being pulled across the universe. We do not mean it is falling freely through empty space toward a single object, the way a planet falls toward a star. We mean it is embedded in a gravitational landscape of extraordinary complexity, responding to the cumulative influence of all the mass concentrations and voids in its surrounding volume, flowing along the gradient of the cosmic gravitational field toward the greatest nearby accumulations of matter. It is less like a planet falling toward a star, and more like a leaf caught in a river, carried not by any single object, but by the entire flow field of the surrounding medium. The medium, in this case, is the cosmic web. The river is the peculiar velocity field, and the source of the current, what drives the flow, is the specific arrangement of overdensities and underdensities that the universe has built up over 13.8 billion years of gravitational evolution from nearly homogeneous initial conditions. To understand what we have found by investigating this motion, we need to understand the history of the investigation itself, because the story of how we discovered what is pulling the Milky Way is as scientifically interesting as the answer. The first clue was the cosmic microwave background dipole, which we have already described, but knowing that we were moving was not the same as knowing why. The CMB dipole gave us the velocity vector, the speed and direction. It did not tell us what was driving it. To answer that question required a different tool, the peculiar velocity survey. A peculiar velocity survey is a systematic attempt to measure the velocities of many individual galaxies relative to the Hubble flow, the smooth expansion of space that carries all galaxies away from each other. By mapping the peculiar velocities of hundreds or thousands of galaxies across a large region of space, you can trace the flow patterns of the local universe, identify convergent zones where flows meet, and map divergent zones where flows separate. The convergent zones correspond to gravitational attractors, the overdense regions toward which matter is flowing. The divergent zones correspond to voids, the underdense regions from which matter is evacuating. The challenge is measuring peculiar velocities with sufficient accuracy to map the flow field. To measure the peculiar velocity of a galaxy, you need to know its true distance independently of its redshift so that you can subtract the Hubble flow contribution and see what is left over. The redshift of a galaxy is the combination of its true peculiar velocity and the Hubble recession velocity, and you cannot separate these two contributions from the redshift alone. You need an independent distance estimate. The two main distance measurement methods used in peculiar velocity surveys of the 20th century were the Tully-Fisher relation for spiral galaxies and the fundamental plane for elliptical galaxies. Both are empirical correlations between observable properties of galaxies and their intrinsic luminosities or sizes, which can be combined with apparent brightness or apparent size to yield distances. Both have individual distance uncertainties of roughly 15 to 20%, which means that peculiar velocities for individual galaxies are noisy. But with large samples, the statistical noise averages down and the underlying flow pattern becomes detectable. The Seven Samurai's 1987 surveys with the fundamental plane method were the breakthrough that identified the Great Attractor as a gravitational anomaly, named it, and established it as the dominant flow convergence in the nearby universe. Subsequent surveys, using both the fundamental plane and the Tully-Fisher relation for larger samples of galaxies, confirmed the direction and approximate amplitude of the flow and began to characterize the mass distribution responsible for it. Over the following 2 decades, as the surveys grew larger and more precise, and as non-optical techniques began to pierce the zone of avoidance, the picture became progressively clearer. The Norma cluster was identified as the dominant structure in the Great Attractor region. The Shapley supercluster was recognized as a major contributor to the long-range peculiar velocity. The combination of these two attractors, plus the developing understanding of the dipole-repeller void, built up into the coherent picture that Tully and colleagues synthesized into the Laniakea definition in 2014, and that Hoffman and colleagues extended with the dipole-repeller in 2017. The Cosmic Flows Project, Brent Tully's multi-decade effort to build the most comprehensive and precise catalog of galaxy distances and peculiar velocities available, was central to both discoveries. The Cosmic Flows 1 catalog appeared in 2008, Cosmic Flows 2 in 2013, the dataset used for Laniakea, Cosmic Flows 3 in 2016, the dataset used for the dipole repeller, Cosmic Flows 4 in 2023, the most extensive and precise yet, continuing to be mined for new insights into the structure of the local universe. Each version of the catalog represented years of observations across multiple telescope facilities and measurement techniques, combined and cross-calibrated to produce a data set of unprecedented breadth and accuracy. The work is ongoing, the map is still being drawn, and each improvement to the catalog, each additional telescope capable of measuring galaxy distances with greater precision, brings us closer to the full picture of the gravitational landscape that shapes the Milky Way's journey through the universe. Expanded Section, Part 3, Full Depth on the Norma Cluster and Zone of Avoidance. The rediscovery of what was hiding behind the galactic plane is one of the more dramatic examples in modern astronomy of the reward that comes from pursuing observations in technically difficult regions that previous surveys had avoided. The zone of avoidance is not a sharp boundary, it is a gradient. At high galactic latitudes, 45 degrees or more above or below the galactic plane, the dust extinction at optical wavelengths is negligible, and the universe appears as clearly as it does anywhere else. As you move toward the plane, the extinction increases gradually, becoming severe at latitudes below about 15 to 20 degrees and essentially total below about 5 degrees in the most obscured directions. The transition is not a sharp line, but a continuous gradient that becomes progressively harder to see through as you approach the equator. Astronomers working near the galactic plane in the 1990s were essentially doing archaeology through fog, trying to identify faint, dust-reddened galaxy images against the bright, confused background of Milky Way stars and nebulae. The photographic techniques available for doing this required plates taken under excellent seeing conditions, followed by careful visual or computational identification of extended objects, which could be distinguished from stars by their slightly fuzzy appearance, followed by spectroscopic follow-up to measure redshifts and confirm that the candidates were indeed background galaxies rather than galactic objects. The particular challenge in the direction of the Great Attractor was that the galactic center itself sits in roughly this direction, only about 30 degrees away from the predicted location of the Great Attractor. The galactic center is the most densely confused part of the galactic plane, containing the highest density of foreground stars, the most intense infrared and radio emission from hot gas and star formation regions, and the most complex and variable extinction map due to the clumpy distribution of molecular clouds. Even working at intermediate latitudes around the galactic center, The background confusion makes galaxy identification extremely difficult. Renée Cran-Cordaweg developed techniques specifically adapted to this environment. Her photographic surveys used wide-field cameras on large aperture telescopes at excellent sites, producing images deep enough to reach the relatively faint galaxies associated with the Great Attractor region while covering enough sky to characterize the overall galaxy distribution. Her team developed criteria for distinguishing faint, reddened galaxies from stars based on their morphological properties, and built up systematic catalogs of new galaxy candidates in the zone of avoidance. The spectroscopic follow-up, measuring redshifts for the galaxy candidates to confirm their distances and identify those associated with the Great Attractor, was conducted at multiple telescopes, including facilities in South Africa, Chile, and Australia. This was particularly efficient for this work, given the location of the Great Attractor in the southern sky. The best observatories for southern sky work, at sites like La Silla in Chile and the South African Astronomical Observatory, were ideally situated to study this region at the low galactic latitudes involved. By the late 1990s, Cran-Cordaweg's team had identified hundreds of new galaxies in the zone of avoidance in the direction of the Great Attractor, and the redshift distribution of these galaxies confirmed a strong concentration at the distance and location expected for the Great Attractor region. The Norma cluster stood out clearly as the dominant structure, with a dense concentration of galaxies at a redshift corresponding to about 220 million light-years. The extended concentration of mass surrounding the cluster, involving multiple additional groups and clusters at similar distances, was also becoming clear. The X-ray characterization of the Norma cluster by Boehringer and the Rosat team provided independent, more physically direct confirmation. The temperature of the intracluster gas in a cluster, measured from the X-ray spectrum, is directly related to the total gravitational mass through the virial theorem because the gas temperature reflects the depth of the gravitational potential well. The temperature of the Norma cluster's intracluster gas was found to be approximately 5 to 6 kiloelectron volts, corresponding to a total cluster mass well in excess of 1 quadrillion solar masses. This was confirmation that the Norma cluster was not just a plausible candidate for the Great Attractor core, but a genuinely extraordinary mass concentration. Subsequent X-ray observations with the more powerful Chandra and XMM Newton satellites in the 2000s and 2010s revealed additional detail about the Norma cluster's structure and dynamics. The X-ray morphology showed evidence of ongoing merging activity, with subclusters in various stages of coalescence and a gas distribution that was not spherically symmetric, indicating that the cluster had not yet reached dynamical equilibrium. This is consistent with the Norma cluster being a relatively young cluster by the standards of rich systems, still actively accumulating mass from the surrounding environment. The jellyfish galaxy ESO 137-001, one of the most spectacular members of the Norma cluster, has become something of an astronomical celebrity in recent years. Hubble Space Telescope images of this galaxy show two prominent trails of ionized gas extending behind it as it plunges through the cluster medium at high velocity, the hot intracluster gas stripping away its interstellar material like a powerful headwind. Chandra observations revealed that the stripped gas glows in X-rays as well as optical emission lines, and detailed analysis of the X-ray emission showed the stripped gas being mixed with the cluster medium at a complex interface where Kelvin-Helmholtz instabilities create turbulent features. Most remarkably, Hubble images revealed blue knots within the stripped gas tails, identified as active star formation regions where the stripped gas has reached the density threshold for gravitational collapse and is forming new stars far from the galaxy itself. ESO 137-001 is manufacturing stars in its own wake, several 100,000 light-years behind itself, a phenomenon that has no parallel in the quieter environment of galaxy groups like the local group. The Norma cluster represents the visible, luminous peak of the gravitational mountain at the center of Laniakea. Its mass, its X-ray brightness, its dynamical activity, all testify to its role as a major node of the cosmic web in our neighborhood. But, as we have emphasized, even the Norma cluster does not tell the whole story of what is pulling the Milky Way. The Great Attractor region as a whole, including the extended mass concentration surrounding the cluster and the multiple associated groups and filaments, provides perhaps half the answer. The other half requires looking much farther afield, to the Shapley supercluster, and then adding the push from behind provided by the dipole repeller. The zone of avoidance investigation has not ended. As survey technology improves, as near-infrared imaging becomes faster and deeper, as radio surveys cover more sky with more sensitivity, the zone of avoidance continues to yield previously unknown structures. The Vela supercluster, a large mass concentration discovered in 2017 by Kron-Korteweg and collaborators using spectroscopic surveys at low galactic latitudes, is a striking example. This structure sits at approximately 800 million light-years distance, largely behind the galactic plane, and was essentially invisible in previous surveys. It may be contributing to the peculiar velocity of the local group in ways that current models do not fully account for. Its full characterization requires continued observation and analysis. The zone of avoidance reminds us that our position inside the Milky Way is both the reason we have detailed knowledge of our host galaxy and the reason we have only partial knowledge of what lies behind it. We live inside the very structure that constrains our view of the most dynamically important region of our cosmic neighborhood. This is not a problem that will ever be entirely solved, but it is one that continued technological development progressively mitigates. Expanded section, Part 5. Additional context on Laniakea. The Laniakea paper's impact on the astronomical community went beyond the specific result about the size and boundaries of our home supercluster. It introduced a new methodology for defining and measuring supercluster boundaries that has since been applied broadly across cosmology and continues to be developed and refined. The watershed method, borrowed from topographical geography and applied to the peculiar velocity field of the universe, provides a definition of supercluster boundaries that is physically motivated, unambiguous given sufficient data quality, and directly connected to the gravitational dynamics of the cosmic web. Unlike previous approaches that defined superclusters by the spatial density of galaxies and required arbitrary choices of smoothing scale and density threshold, the watershed method has a clean physical interpretation. A supercluster is a coherent gravitational basin, a volume of space whose contents are gravitationally coupled to the same ultimate attractor. The method also has the advantage of being directly comparable to the predictions of cosmological simulations. A simulation that starts with known initial conditions and evolves forward under known physics produces a three-dimensional density and velocity field that can be analyzed with the same watershed algorithm applied to observational data. The size, shape, and statistical properties of the supercluster basins identified in simulations can be compared directly to those identified in observations, providing a test of whether the cosmological model correctly predicts the structure of the local universe. Initial comparisons of this kind, made using the Cosmic Flows 2 data and the Laniakea definition, found broad agreement between the observed Laniakea structure and the supercluster basins found in cosmological simulations, with the standard model parameters. This was reassuring, suggesting that Laniakea is a typical structure in a universe with the measured cosmological parameters rather than an anomalously large or unusual feature. More recent analyses using the Cosmic Flows 4 catalog, which is substantially larger and more precise than Cosmic Flows 2, have begun to reveal additional complexity. Some analyses find that when galaxy groups, rather than individual galaxies, are used as tracers of the velocity field, the Laniakea basin appears as part of a larger structure, possibly the Shapley basin, rather than as an independent supercluster. This suggests that the question of whether Laniakea is a distinct entity or a substructure of a larger complex is genuinely sensitive to the way the velocity field is reconstructed and how group membership is defined. This is not a failure of the method or a contradiction of the 2014 result. It reflects the fact that the cosmic web has a hierarchical structure, with basins nested within larger basins, and that the exact boundaries depend on the scale at which you are looking. Laniakea is a real, well-defined structure at the scale of a few hundred million light-years. At the scale of a billion light-years, it may be a substructure of a larger basin centered on Shapley. Both descriptions can be simultaneously true at their respective scales, just as a valley in a mountain range is simultaneously a distinct feature of the landscape and a subfeature of the larger basin containing the range. The Cosmic Flows project continues to expand the database of galaxy distances and peculiar velocities. The Cosmic Flows 4 catalog, published in 2023 by Tully and collaborators, contains distance measurements for over 55,000 individual galaxies, a factor of roughly 7 more than cosmic flows 2 used for Laniakea. The improved statistical power and greater depth of coverage allow the velocity field to be reconstructed with higher resolution and to greater distances, progressively filling in the map of the local cosmic web. Upcoming surveys promise even more dramatic improvements. The Dark Energy Spectroscopic Instrument, DESI, operating at the Kitt Peak National Observatory in Arizona, is conducting one of the most ambitious spectroscopic surveys ever attempted, targeting tens of millions of galaxies over a 5-year period. DESI's redshift measurements, combined with photometric distance estimates, will provide peculiar velocity data for hundreds of thousands of galaxies, an order of magnitude improvement over the current cosmic flows catalogs. The Rubin Observatory, currently being commissioned in Chile, will produce the deepest wide-field imaging survey ever conducted, and will enable photometric distance estimates for hundreds of millions of galaxies. The Euclid Space Telescope, launched in 2023 by ESA, is conducting a wide-area spectroscopic and photometric survey that will characterize the large-scale structure of the universe to unprecedented depth. With these facilities, the map of the local cosmic web will be refined dramatically in the coming decade. The boundaries of Laniakea will be pinned down with much greater precision. The contribution of the Vela supercluster and other recently discovered structures to the peculiar velocity of the local group will be characterized. The full mass inventory of the Great Attractor region and the Shapley supercluster will be determined, and the broader architecture of the cosmic web within a few billion light-years of the Milky Way will be mapped in far greater detail than is currently possible. This is genuinely exciting science, not because the current picture is wrong, but because it is incomplete, and the tools to complete it are either already in operation or coming online in the near future. We are living through the era when the basic facts of our cosmic address are being established from scratch, with each new survey revealing previously unknown features of the landscape. Expanded section, Part 7. Deeper analysis of the dipole repeller. The discovery of the dipole repeller raised a question that goes beyond the specific dynamics of the Milky Way's motion. How common are such large voids in the nearby universe, and how significant are they as drivers of peculiar velocities more generally? The answer from cosmological simulations and large-scale surveys is that large voids are extremely common. In fact, voids dominate the volume of the universe. Surveys like the Sloan Digital Sky Survey have mapped thousands of voids in the galaxy distribution, ranging from relatively small supervoids, a few tens of millions of light-years in diameter, to truly enormous voids, hundreds of millions of light-years across. The largest known voids, like the Bootes void discovered in 1981 by Robert Kirshner and colleagues, are vast near-emptiness extending 300 to 400 million light-years in extent. The dipole repeller is significant not because large voids are rare, but because it is the specific large void that happens to be located in approximately the right direction and distance to be contributing substantially to the peculiar velocity of the Milky Way. Its position, roughly opposite to the Shapley supercluster as seen from our location, means that its effective repulsive contribution adds constructively to Shapley's attractive contribution rather than canceling it. The alignment is not coincidental in some cosmic conspiracy sense. It simply reflects the specific arrangement of overdensities and underdensities in our particular neighborhood, which is itself a random realization of the statistical distribution of cosmic web features. Understanding voids as gravitational structures requires thinking about them carefully. A void is not empty space in the absolute sense. Even the emptiest voids detected in galaxy surveys contain some galaxies, just far fewer than the cosmic average. The void's defining characteristic is not total emptiness, but significant underdensity relative to the average. Matter within a void streams outward along the void's edges into the surrounding filaments and clusters, driven by the gravitational imbalance between the sparse interior and the denser surroundings. This outward streaming produces a characteristic velocity pattern around a void that is distinct from the inflow pattern around an overdensity. Galaxies near the edge of a void show peculiar velocities directed away from the void's center, toward the surrounding denser regions. Galaxies farther from the void, but still within its gravitational sphere of influence, show smaller but still measurable outward motions. The void acts as a gravitational source of divergent flow, and the total magnitude of this divergent flow is proportional to the void's mass deficit, the total amount of mass that is missing relative to the average density. For the dipole repeller, the mass deficit is substantial. Although the precise characterization of the void is still being refined as surveys improve, the reconstruction by Hoffman and colleagues suggests that it represents a significant underdensity over a large volume, with a mass deficit comparable in gravitational influence to the mass excess of the Shapley supercluster at its comparable distance. This is why the push from the dipole repeller is comparable in magnitude to the pull from Shapley. Both structures have comparable gravitational influence from comparable distances on opposite sides of the Milky Way. The identification of the dipole repeller also has implications for how we think about the standard cosmological model. The model predicts a specific statistical distribution of void sizes, depths, and spatial correlations. The existence of a void of the dipole repeller's apparent characteristics in the appropriate location to be a major driver of the local group's peculiar velocity is consistent with the model's predictions, but the precise mass deficit of the void and its exact spatial extent are additional constraints on the model that can be compared to simulations. Future surveys will directly map the galaxy population within the dipole repeller, confirming its extent and characterizing the sparse galaxy distribution within it. The few galaxies expected to exist in such a void should be identifiable in sufficiently deep surveys at optical, near-infrared, and radio wavelengths. These galaxies, isolated in an underdense environment far from the rich filaments and clusters where most galaxy formation has been concentrated, may have unusual properties reflecting their unusual environment. Studies of galaxies in void environments have found evidence for different evolutionary histories compared to cluster or filament galaxies, with void galaxies tending to be bluer, more gas-rich, and less disturbed by interactions than their counterparts in denser regions. The dipole repeller's galaxies, when finally mapped in detail, may therefore provide a unique laboratory for studying how galaxy evolution differs in the extreme underdensity of a supervoid, far from the gravitational tide of the surrounding web. Expanded section. Part 11. The philosophical depth of the story. What does it mean to know that you are being pulled through the universe at 627 kilometers per second towards structures whose names were coined within the lifetimes of people currently alive? This is not a rhetorical question. It is a genuinely new kind of knowledge that humanity has only recently acquired, and its implications for how we understand our place in the cosmos are still being absorbed. For most of human history, the question of where the Milky Way is in the universe was not even well posed. Before 1924, when Edwin Hubble's observations of Cepheid variable stars in the Andromeda Nebula confirmed that it was a separate galaxy comparable to our own Milky Way, many astronomers doubted that other galaxies existed at all. The Milky Way was thought by some to be the entire universe, or at least its dominant structure. The concept of the cosmos as a vast collection of galaxies, billions of them, arrayed in a hierarchical structure of groups and clusters and superclusters stretching across billions of light-years, did not exist in a scientifically established form until the second half of the 20th century. And even once the existence of a universe full of galaxies was established, the question of how they were organized at the largest scales, the question of whether the Milky Way was moving relative to those structures and why, remained unanswerable until the tools to measure galaxy peculiar velocities were developed and applied. The CMB dipole, the observational evidence for our peculiar velocity, was first measured in the early 1970s and established definitively by the mid-1980s. The Great Attractor was named in 1987. The Norma cluster was identified as the core structure in the mid-1990s. Laniakea was defined in 2014. The dipole repeller was discovered in 2017. These are not ancient facts. They are contemporary discoveries. The question of what our cosmic address is, of what supercluster we live in, and what structures are shaping our trajectory through the universe, is a question whose answer has been known, in its current form, for less than a decade. This is remarkable for an era of science that sometimes presents itself as knowing the fundamentals. In particle physics, the Standard Model has been established for decades. In gravitational physics, general relativity has been tested to extraordinary precision. In stellar physics, the processes powering stars from hydrogen fusion to final collapse are well understood. These are mature fields, complete in their basic frameworks, even if details remain to be worked out. The large-scale structure of the local universe, by contrast, is a field that is still in the process of establishing its basic framework. The map of the cosmic web within a billion light-years is still being drawn. New major structures are still being discovered. The precise contributions of different structures to the peculiar velocities of galaxies in our neighborhood are still being quantified. The question of whether Laniakea is a distinct supercluster or a tributary of the Shapley Basin is still being debated. The zone of avoidance still hides structures that have not been identified. In this sense, investigating what pulls the Milky Way across the universe is a live, ongoing scientific enterprise, rather than a matter of looking up established answers in a textbook. The people doing this work are genuinely discovering things that have never been known before. The maps they are drawing are the first maps of their kind. The structures they are naming are being named for the first time in the history of intelligent life in this part of the universe. There is something that should feel important about that to anyone who thinks carefully about it. We are among the first generation of beings in this part of the cosmos to know that they are in a river, to know what the river is called, to have names for the mountains and valleys of the gravitational landscape. This knowledge has been earned through decades of painstaking observation, technological development, and theoretical work by hundreds of scientists working across multiple countries and generations. It represents a genuine expansion of what it means to know where you are. The Milky Way's peculiar velocity of 627 kilometers per second toward the constellation Centaurus is a fact about the universe. Laniakea is a real structure. The Great Attractor is a real gravitational feature. The Shapley supercluster is the most massive known structure in our cosmic neighborhood. The dipole repeller is a real void. These are not hypothetical constructs or artifacts of particular observational methods. They are features of the actual universe, shaped by the same physical laws that govern everything from subatomic particles to the large-scale expansion of space, revealed to human understanding through the patient accumulation of evidence. And we, right now, in the current moment of history, are among the first members of any species anywhere in this part of the universe to know this. That fact deserves to be held with some appreciation. The river has always been here. We have only just found out that we are in it. Expanded section, Part 2. The technical achievement of peculiar velocities surveys. The story of how we mapped the flow of the Milky Way through the cosmos is also, at a deeper level, a story about the development of methods for measuring distances to galaxies across hundreds of millions of light-years with useful precision, and about the decades of effort that the builders of those methods invested. Distance measurement in astronomy is one of the most technically demanding and historically contested areas of the entire field. For nearby objects, direct geometric methods work beautifully. Parallax, the apparent shift in the position of a nearby star against the background of distant stars as the Earth orbits the Sun, provides precise distances to stars within a few thousand light-years. But parallax becomes unusable for objects much beyond a few thousand light-years, because the angular shifts become too small to measure with the precision available. For extragalactic objects, hundreds of millions to billions of light-years away, direct geometric methods are completely out of reach. What astronomers use instead is a hierarchy of distance indicators, each calibrated against the previous level, building up a so-called cosmic distance ladder. Cepheid variable stars, whose pulsation period is tightly correlated with their intrinsic luminosity, provide distances to galaxies within about 100 million light-years. Type 1a supernovae, the explosions of accreting white dwarf stars, whose peak luminosity is well calibrated, extend the ladder to billions of light-years. And at intermediate distances, in the hundreds of millions of light-years range most relevant to the peculiar velocity surveys we have been discussing, the main tools are the Tully-Fisher relation and the fundamental plane. The Tully-Fisher relation was discovered by R. Brent Tully and J. Rowan and J. Richard Fisher in 1977. It states that the rotational velocity of a spiral galaxy, measured from the width of its 21-centimeter hydrogen emission line, is tightly correlated with the galaxy's intrinsic luminosity. More rapidly rotating galaxies are more luminous. The physical basis for this correlation is that both the luminosity and the rotation velocity reflect the total mass of the galaxy, with more massive galaxies both rotating faster and containing more stars. By measuring the 21-centimeter line width of a spiral galaxy, you can estimate its intrinsic luminosity, and comparing that to the apparent brightness gives the distance. The scatter in the relation limits individual distance accuracy to about 15 to 20%, but for statistical surveys of thousands of galaxies, this is sufficient to extract meaningful flow patterns. The fundamental plane relation for elliptical galaxies was developed somewhat later in the 1980s by a series of groups including those around Sandra Faber and her collaborators. It is a three-way correlation between the effective radius of the galaxy, its mean surface brightness within that radius, and its internal velocity dispersion, measured from spectral line widths. The physical basis again relates to the virial theorem and the dynamical equilibrium of the stellar system. The accuracy per galaxy is similar to the Tully-Fisher relation. Both methods require careful calibration, which means anchoring the relation at nearby, well-determined distances measured by more precise methods like Cepheids or Type 1a supernovae, and then extrapolating to larger distances where those primary indicators cannot be applied. The calibration is always uncertain at some level, and different calibration choices can lead to systematic offsets between distant surveys conducted by different groups. This is the reason that the Hubble constant, the proportionality between recession velocity and distance that sets the scale of the universe, has been the subject of significant controversy even in recent years, with different measurement methods yielding somewhat different values. For peculiar velocity surveys, the systematic uncertainties in the distance scale matter less than the relative precision of the distances within the survey. What matters for identifying the flow pattern is whether galaxy A is slightly closer or farther than galaxy B relative to what the Hubble flow predicts, not whether the absolute distance scale is calibrated to 1% or 3%. The relative precision, which determines how well peculiar velocities can be isolated from the Hubble recession, is more critical than the absolute calibration. This is why peculiar velocity surveys can be internally consistent and scientifically valuable, even when the absolute Hubble constant is uncertain. The Cosmic Flows project represents the culmination of decades of effort to combine all available distance measurement methods into a single, carefully cross-calibrated catalog of galaxy distances and peculiar velocities. Tully began building the foundations of this project in the 1970s and 1980s, with his own Tully-Fisher measurements of hundreds of galaxies, working at first with photographic plates at the Canada-France-Hawaii telescope on Mauna Kea, and later with digital detectors at multiple facilities. Over time, the catalog expanded to include fundamental plane measurements for elliptical galaxies, surface brightness fluctuation distances for early type galaxies, Type 1, A supernova distances, and distances from the Sunyaev-Zeldovich effect for galaxy clusters. Each distance method has its own systematic errors and its own selection biases, favoring galaxies of particular types or in particular environments. Combining multiple methods into a single catalog requires extensive cross-calibration work to ensure that distances measured by one method agree with those measured by another at the same galaxies. This cross-calibration is technically demanding and is itself a research program, not just a bookkeeping exercise. The Cosmic Flows 4 catalog, published in 2023, represents the current state of the art. It contains distances for over 55,000 individual galaxies, covering a volume extending to about 600 million light-years in most directions and somewhat farther in directions with more data. At this depth and spatial coverage, the peculiar velocity field of the nearby universe is constrained well enough to identify all the major attractor and repeller features, including the Great Attractor, the Shapley supercluster, the dipole repeller, and the emerging picture of the South Pole Wall and Vela supercluster. The practical challenge of building such a catalog involves observations at multiple telescopes over many years. Measuring 21-centimeter line widths for thousands of spiral galaxies requires radio telescope time at facilities like the Parkes 64-meter telescope in Australia, Arecibo before its collapse in 2020, and now the 500-meter aperture spherical telescope in China, the largest single-dish radio telescope ever built, which is contributing substantially to the next generation of cosmic flows measurements. Measuring velocity dispersions and photometric properties for thousands of elliptical galaxies requires optical telescope time at facilities equipped with multi-object spectrographs capable of efficiently measuring multiple galaxies simultaneously. The effort required to assemble these datasets over decades, combining observations from dozens of telescope facilities, working through the systematic cross-calibrations and building the software and statistical methodology to extract the peculiar velocity field from the combined data, represents one of the most sustained long-term observational programs in extragalactic astronomy. It has produced, over its arc, a transformation in our understanding of the large-scale dynamics of the local universe that could not have been achieved by any single observation or any shorter-term program. The fact that this program's results, Laniakea in 2014 and the Dipole Repeller in 2017, have entered popular culture and science communication as widely recognized discoveries testifies to both the scientific significance of the findings and the effectiveness with which they were communicated. Tully, Courtois, Hoffman, and Pomered found effective ways to visualize and explain their results, producing animations and simulations of the galaxy flow fields that made the abstract three-dimensional structures viscerally comprehensible to a general audience. The Laniakea visualization, showing galaxy flow lines sweeping gracefully inward toward the Great Attractor, has been viewed millions of times and has become one of the iconic cosmological images of the 21st century. The next generation of cosmic flows measurements, driven by DESI, the Rubin Observatory, and potentially the Square Kilometre Array radio telescope currently under construction in South Africa and Australia, will extend the catalog to much greater depths and numbers than are currently achievable. The Square Kilometre Array in particular, expected to become fully operational in the late 2020s, will be able to measure 21-centimeter line widths for millions of spiral galaxies across much of the sky, providing a peculiar velocity catalog, orders of magnitude larger than the current cosmic flows 4, and extending to distances where the connections between the local cosmic web and the broader universe become apparent. With these tools, the map of what is pulling the Milky Way across the universe will be drawn with a precision and completeness that the current generation of surveys cannot match. The current picture, extraordinary as it is relative to what was known 50 years ago, is itself a stepping stone to a still more detailed and complete understanding. Expanded section, the zone of avoidance, how we learn to see the invisible. The history of astronomy has many examples of important regions of the sky being initially inaccessible to observation and then opened up by technological advances. The galactic center was essentially invisible in optical wavelengths until radio and infrared observations in the 20th century revealed it. The dust-enshrouded star-forming regions where new stars are born were unknown until infrared and millimeter wavelength observations could penetrate the dust. And the zone of avoidance, the band of sky where the Milky Way's disk blocks the view of more distant galaxies, was opened up progressively through the 1980s and 1990s as a variety of non-optical techniques were brought to bear on it. Each technology that could pierce the zone of avoidance revealed something new. Radio surveys at 21 centimeters were among the first effective tools. Since dust is essentially transparent to radio waves at this wavelength, 21-centimeter surveys could detect the hydrogen emission from galaxies at low galactic latitudes that were completely invisible to optical telescopes. The IRAS infrared satellite revealed dust-heated galaxies at low galactic latitudes. ROSAT X-ray maps revealed the hot gas in clusters. The combination of all these approaches built a progressively more complete picture of what lay behind the dust, and the picture consistently confirmed what the peculiar velocity surveys had been predicting: a substantial mass concentration in the direction of the predicted Great Attractor, dominated by the Norma cluster, with additional filamentary structures connecting it to the surrounding cosmic web. The zone of avoidance investigation also produced some unexpected discoveries beyond the Great Attractor itself. The Vela supercluster mentioned earlier was identified largely because a team led by René Cron-Cordaweg was willing to push redshift surveys to very low galactic latitudes where the absorption was severe but not total. The Vela supercluster extends across the zone of avoidance and is only partially visible on either side of the galactic plane, requiring surveys at low latitudes to trace its extent and characterize its mass. The Cosmic Flows surveys and the Zone of Avoidance explorations are complementary programs. The Cosmic Flows surveys measure the peculiar velocities that trace the gravitational field and identify the attractor and repeller structures. The Zone of Avoidance surveys directly identify the galaxy clusters and superclusters hidden behind the galactic plane that are contributing to those flows but cannot be seen in standard sky surveys. Together, these programs are building the complete picture of the local cosmic web, that explains the Milky Way's journey through the universe. The scientific community has learned, through the zone of avoidance work, that some of the most scientifically important regions of the sky are precisely the ones most difficult to observe. This lesson has been generalized into a broader principle. The most interesting astronomy often happens at the frontiers of observational capability, in the regions where instruments are pushed hardest and where the effort required is greatest. The zone of avoidance is a specific example of this principle, but the same lesson applies to the most distant galaxies, the most obscured regions of the interstellar medium, and the faintest signals in any wavelength domain. Science advances most rapidly at the edges of what is currently possible. Closing synthesis, the river and its meaning. Everything in this video can be condensed into a single image, though the image needs time to assemble itself properly before it can be appreciated. Imagine the universe at the scale of hundreds of millions of light years. The cosmic web fills the scene, bright nodes where clusters and superclusters have assembled, long filaments of galaxies and dark matter connecting the nodes, broad sheets marking the boundaries between voids, and vast, dark voids occupying most of the volume. The scene is animated because nothing in the universe is still. Galaxies flow along the filaments toward the nodes. Matter drains from the voids into the surrounding structure. The nodes grow slowly as they accumulate infalling material. In this scene, find the Shapley supercluster, a bright concentration of thousands of galaxies roughly 650 million light-years in one direction. Find the dipole-repeller void in roughly the opposite direction, a dark region notable for its absence of the galaxies that fill the surrounding landscape. Between these two, flowing steadily from the void toward the attractor in response to the gravitational imbalance between them, find the Milky Way, a small spiral galaxy near the edge of the Laniakea supercluster, participating in the same flow that carries 100,000 galaxies toward the same gravitational center. The Milky Way is one data point in this flow field, one galaxy among hundreds of thousands, all participating in the same directed motion. Its peculiar velocity of 627 kilometers per second is the cumulative result of 10 billion years of gravitational acceleration by this landscape, encoded in the motion of 100 billion stars and an even greater mass of invisible dark matter, all moving together in response to the specific arrangement of matter and emptiness that defines our cosmic neighborhood. The journey has no arrival. Dark energy will prevent any convergence with the Great Attractor or Shapley within any cosmological timescale relevant to the survival of complex structures. The river flows toward a destination that continuously recedes as the universe expands. But the river is real, the current is measurable, and the landscape through which it flows has been mapped for the first time in the history of intelligence in this part of the cosmos. This is what science does at its best. It takes invisible things and makes them legible. It takes forces operating across scales completely inaccessible to human senses and translates them into knowledge. It takes 627 kilometers per second of invisible motion through a universe with no perceptible landmark and turns it into a story with characters, structures, distances, and names. Laniakea, the Great Attractor, the Shapley supercluster, the dipole repeller. These are not just names in a catalog. They are the features of the gravitational landscape that has been shaping the Milky Way's trajectory through the cosmos since before the Earth existed. They are the answer, worked out over decades by hundreds of scientists with telescopes on every continent and in orbit above the atmosphere, to the question that the faint temperature asymmetry of the cosmic microwave background first posed. What is the Milky Way moving toward, and why? Now you know. The river is real, you are in it, and you always have been. Deep expansion, the physics of why distance doesn't kill the pull. One of the most counterintuitive aspects of cosmic dynamics, and one worth dwelling on carefully because it resolves a genuine puzzle about the scale of the forces involved, is the question of why the gravitational pull of structures hundreds of millions of light years away can produce peculiar velocities of hundreds of kilometers per second in something as massive as an entire galaxy. The answer, as we touched on earlier, is time. But spelling out the full physics of this makes the answer much more satisfying than the simple summary suggests. Newtonian gravity tells us that the force between two objects falls as the inverse square of their distance. This means that the gravitational acceleration of the Milky Way toward the Shapley supercluster, at 650 million light-years distance, it is extraordinarily small. To calculate it roughly, The mass of Shapley is approximately 10 to the 16th power solar masses, which in kilograms is about 2 times 10 to the 46th kilograms. The distance of 650 million light-years is approximately 6 times 10 to the 24th meters. The gravitational acceleration is g times bolsa divided by distance squared, where g is Newton's constant. Plugging in the numbers gives an acceleration of roughly 3 times 10 to the minus 14th meters per second squared. That is 0.0000000000003 meters per second squared. Essentially nothing on any human timescale. But now multiply this by the age of the universe, roughly 4 times 10 to the 17th seconds. The resulting velocity is approximately 12,000 meters per second, or 12 kilometers per second. This is of the right order of magnitude for a contribution from Shapley to the local group's peculiar velocity, given various complications, though the actual calculation is much more involved because the distance has been changing as the universe expands and the density field has been evolving. The key point is that even a force of 10 to the minus 14th meters per second squared, accumulated over the age of the universe, produces a velocity of thousands of meters per second. Tiny accelerations, multiplied by cosmic time, become substantial velocities. The universe is a machine for converting minuscule forces into large motions, simply by running for an incomprehensibly long time. This is also why the peculiar velocity of the Milky Way is a record of the entire gravitational history of our region, not just the present configuration. The force of gravity from Shapley today is tiny, but the force 10 billion years ago, when the universe was smaller and Shapley was correspondingly closer in co-moving terms, and when the internal density contrast of Shapley may have been building up toward its present value, was different. The peculiar velocity we measure today is the integral of all the forces that have acted over cosmic time, not a snapshot of the current instantaneous force. This is why mapping peculiar velocities provides information about the time-integrated mass distribution, including the dark matter, rather than just the instantaneous gravitational field. There is also the important effect that the peculiar velocity is not just produced by Shapley alone. It is the vector sum of contributions from every mass concentration and every void in the entire surrounding volume, each contributing a small component in its own direction, the whole summing to the observed 627 kilometers per second towards Centaurus. Shapley and the dipole repeller are the dominant contributors because they are the most extreme features of the density field in the relevant volume, but hundreds of other structures, smaller and closer, also contribute at lower amplitudes. The beautiful thing about the watershed method used to define Laniakea is that it captures this distributed nature of the gravitational influence. The basin of attraction defined by the velocity flows is not just a region around a single dominant attractor. It is the full volume of space from which all the gravitational contributions, integrated over cosmic time, conspire to direct matter toward the same ultimate destination. The watershed surface marks the boundary where those integrated contributions shift from pointing inward to pointing outward, where the net effect of all the surrounding mass flips from pulling toward the Laniakea center to pulling toward some other basin. This is a more complete and physically meaningful definition of gravitational membership in a structure than any position-based criterion could provide. The enormous volume of Laniakea, 520 million light-years across, reflects the fact that the gravitational reach of the great attractor and the surrounding mass distribution is genuinely this large. It is not an arbitrary choice of boundary or a consequence of drawing a circle with a large enough radius. It is a physical statement about where the dominant gravitational influence switches from the Laniakea center to competing basins, as determined by the actual, measured three-dimensional velocity field of the local universe. Understanding this also helps clarify why the Milky Way's peculiar velocity cannot be fully explained by any single nearby structure. No single galaxy cluster, however massive, sitting within a few hundred million light-years, is massive enough or close enough to be responsible for 627 kilometers per second of peculiar motion when acting alone. The peculiar velocity is the result of an extended distribution of mass, the entire Laniakea structure, and the Shapley supercluster beyond it, acting over the full age of cosmic structure formation. It is a collective phenomenon, not a point source attraction. This is one of the ways that the investigation of what pulls the Milky Way illuminates the broader physics of the cosmos. It demonstrates concretely, through a specific measurable example, that the universe is dynamically connected on scales that dwarf anything accessible to direct human experience. The motions of galaxies are not local phenomena. They are cosmic phenomena, shaped by the distribution of matter across volumes measured in hundreds of millions of light-years, by forces that have been acting for billions of years, by the specific arrangement of the cosmic web that grew from quantum fluctuations in the first moments of the universe's existence. The Milky Way's 627 kilometers per second is a measurement of all of this. It is a compression of cosmological history into a single vector, legible if you know the language, and the language is the physics of gravity in an expanding universe structured by dark matter and dark energy. The question that remains open after everything we have covered, one genuinely open question deserves its own moment of attention, because it is the honest frontier of current knowledge. We know the dominant contributors to the Milky Way's peculiar motion, the Great Attractor, the Shapley supercluster, the dipole repeller. We have characterized these with reasonable precision using the cosmic flows catalogs and the watershed and potential field reconstruction methods. The model works. When you include these structures in the calculation, you can reproduce the observed peculiar velocity in direction and approximate magnitude. But the models are not perfect. There are residuals, small differences between the predicted and observed peculiar velocities of galaxies in our neighborhood, and these residuals could be noise in the data, could be limitations of the modeling methods, or could be genuine signal from structures not yet fully characterized. The most prominent candidate for a missing structure is the collection of superclusters and filaments that lie at distances of 1 to 2 billion light-years from the Milky Way, beyond the current depth of the cosmic flows surveys. At these distances, the gravitational influence of any structure is weaker because of the greater distance. But structures at this range have still had billions of years to accumulate gravitational momentum in the direction of the flow. If there are large, previously unmapped mass concentrations at 1 to 1.5 billion light-years in roughly the Shapley direction, their contribution to the local group's peculiar velocity could be non-negligible. This is exactly the regime where the next generation of surveys will provide new information. DESI, Euclid, and the Rubin Observatory will characterize the galaxy distribution and peculiar velocity field to depths of 2 to 5 billion light-years, far beyond what cosmic flows 4 can achieve. If there are significant mass concentrations at these distances contributing to the local flow, they will show up in the improved data sets. The possibility also remains that the dipole repeller is not perfectly characterized. Its mass deficit has been estimated from the flow field reconstruction, but a direct inventory of the galaxy population within the void and the surrounding structure would provide a more robust characterization. Future deep surveys covering the relevant region of sky will progressively fill in this picture. And there is always the possibility, carefully considered in the discussion of dark flow and the work of Kashlinsky and colleagues, that there is some contribution to the peculiar velocity from structures at truly enormous distances, potentially beyond the reach of any survey that could be conducted with foreseeable technology. This possibility remains scientifically open, even if the specific dark flow claim has not been confirmed. The question of what, if anything, beyond the visible cosmic web is shaping the dynamics of the local universe is one that may never be fully answerable, given the fundamental observational limits imposed by the cosmological horizon. But the question is well posed, the methods for investigating it are increasingly powerful, and the community working on it is actively pushing the frontier. The river will be mapped more completely in the coming decades than it has been in the decades just past. The answer to what is pulling the Milky Way across the universe will become more precise, more detailed, and more complete than anything we currently have. We will learn more. We always do when we keep looking. A final note on the scale of knowing. There is a kind of vertigo that comes from really sitting with what has been described in this video, and it is worth not rushing past it. You are on a planet orbiting a star. The star is one of somewhere between 100 and 400 billion stars in the Milky Way galaxy. The Milky Way is one of roughly 100,000 galaxies in a supercluster called Laniakea, which extends 520 million light-years from edge to edge. Laniakea flows toward a gravitational center called the Great Attractor, which is itself being drawn toward the Shapley supercluster 650 million light-years away. Behind the Milky Way, in the opposite direction, a vast underdense region called the dipole repeller pushes with comparable force to Shapley's pull. The net result is 627 kilometers per second of directed motion through the cosmos that you have never felt and can never feel. But that is as real and measurable as the temperature of a star or the mass of a black hole. All of this, the entire architecture of our cosmic neighborhood, from Laniakea's 100 quadrillion solar masses to the void behind us, has been known to humanity for less than a decade in any complete form. The naming of Laniakea was 2014. The identification of the dipole repeller was 2017. The South Pole Wall was 2020. The full characterization of the Shapley supercluster and its contributions to local flows has been ongoing through the 2010s and into the 2020s. This means you are alive in the first generation of humanity that knows where in the universe it lives, not just in the trivial sense of knowing which galaxy or which arm of which galaxy, but in the deepest structural sense, which supercluster, which gravitational basin, which cosmic river, flowing in which direction, for which reasons, toward which extraordinary concentrations of matter. No generation before yours had access to this knowledge. It did not exist, and now it does. It was won through the patient work of scientists with telescopes, satellites, supercomputers, and decades of accumulated effort, and it is yours simply by paying attention. The river runs. It has always run. And now you know that you are in it. The river runs. The current carries everything. And we, finally, know the shape of the bed through which it flows, the mountains rising on one side, the void opening on the other, and the long, slow, beautiful, inevitable drift of 100,000 galaxies moving together toward home.